Welcome back, Night Wanderer. Tonight, we're turning our gaze upward to Earth's oldest companion, the Moon. That pale disk that's watched over our world for billions of years, silent and patient in the darkness above. If you haven't already, consider subscribing to the channel. It helps us create more of these quiet journeys through science, and it means you'll never miss a night of gentle learning. Now, let's begin. The Moon is Earth's only permanent natural satellite, orbiting our planet at an average distance of 238,855 miles. Look up on any clear night, and there it is, the Moon, hanging in the darkness like a lantern someone forgot to turn off. But have you ever stopped to wonder just how far away that light really is? 238,855 miles. It's a number so large it almost loses meaning, doesn't it? Here's one way to think about it. If you could somehow gather up all the other planets in our solar system, Mercury, Venus, Mars, Jupiter, Saturn, Uranus, Neptune, and line them up in a row between Earth and the Moon, they would all fit, every single one, with room to spare. That's how far our companion sits from us, separated by a gulf of space vast enough to contain entire worlds. And yet, despite this enormous distance, the Moon has never left us. Not once in the 4.5 billion years since it formed. It circles our planet with a faithfulness that's almost poetic, keeping watch over our days and nights, pulling at our oceans, steadying our spin. Perhaps that's why we've always felt such a connection to it, this distant thing that somehow feels close, familiar, like an old friend who never quite comes inside but is always there, just beyond the door. The Moon is slowly drifting away from Earth at a rate of about 1.5 inches per year. But here's something most people don't know. That old friend is quietly walking away. Not quickly. Nothing in the cosmos happens quickly, but steadily, reliably, about 1.5 inches every year. It's been doing this since the beginning, since the day it formed, and it will keep doing it until the sun dies and takes us both with it. 1.5 inches doesn't sound like much, does it? It's less than the length of your thumb. But multiply that by millions of years, by hundreds of millions, by billions, and suddenly you're talking about real distance. In 1 billion years, if anyone is still here to see it, the Moon will be tens of thousands of miles farther away than it is now. It will look smaller in the sky. The tides will be gentler. Solar eclipses, those perfect alignments we're so lucky to witness, will no longer be total. The Moon's shadow will fall short of Earth, and we'll see a ring of sunlight around its edge. Never darkness, never that perfect covering. Maybe there's something melancholy about that. The idea of slow separation, inevitable and unchangeable. Or maybe it's just the way things are. The universe doesn't do forever, not really. Everything drifts, everything changes, even the things that seem most permanent. The same side of the Moon always faces Earth, a phenomenon called tidal locking. The Moon has a face it shows us and a face it hides. Always the same presentation, like a person who never quite turns around. This isn't coincidence or choice, it's physics, something called tidal locking, the result of billions of years of gravitational interaction between Earth and its companion. Imagine the Moon billions of years ago spinning freely, showing all of itself to Earth as it rotated, but Earth's gravity tugged at it, creating bulges in the Moon's shape, and those bulges created friction, and that friction gradually slowed the Moon's rotation until eventually it stopped spinning relative to Earth. Now it rotates exactly once for every orbit it makes, keeping the same hemisphere eternally facing us. For most of human history, we had no idea what the far side looked like. We could theorize, imagine, dream about it, but we couldn't see it. Not until 1959, when a Soviet spacecraft called Luna 3 swung around behind the moon and snapped photographs of that hidden hemisphere. And you know what they found? Not alien bases or secret landscapes, just more moon. Cratered, ancient, unfamiliar but recognizable. The mystery solved in a way, but somehow that makes it more poignant. The hidden face wasn't hiding anything at all, it was just there, unseen for all those eons, waiting for someone to finally look. The moon formed approximately 4.5 billion years ago, shortly after Earth itself came into existence. The moon is old. Not just old in the way grandparents are old, or ancient civilizations, or even dinosaur bones. Old in a way that's hard to wrap your mind around. 4.5 billion years. That's roughly the same age as Earth itself. Give or take a few tens of millions of years, a rounding error on cosmic timescales. Think about what that means. The moon was already here when Earth was still a molten ball of rock, too hot for oceans, too hostile for life. It watched, if watching is the right word for a lifeless sphere of stone, as our planet cooled, as the first rains fell and filled the basins that would become seas. It was there when the first simple organisms emerged in those seas, when they learned to photosynthesize, when they crawled onto land. It saw the dinosaurs rise and fall. It saw ice ages come and go. It saw the first humans look up and wonder what that bright thing in the sky was. The moon has been our companion for almost the entire story of our planet. Every chapter, every era, every extinction and flourishing. If stones could remember, the moon would hold memories stretching back to before memory had meaning, and it's still here, still circling, still watching, patient as only geological time can be. The leading theory suggests the moon was created when a Mars-sized object called Theia collided with early Earth. So where did the moon come from? For a long time, we didn't know. We had theories. Maybe it formed alongside Earth. Maybe it was captured by Earth's gravity as it wandered past. Maybe it somehow budded off from our planet like a cell dividing. But none of these quite fit the evidence. The leading theory now is more violent, more dramatic. Scientists believe that early in Earth's history, when our planet was young and still forming, another world, about the size of Mars given the name Theia, crashed into us. Not a glancing blow, but a direct, catastrophic impact at tremendous speed. The collision vaporized both worlds' outer layers, sending massive plumes of molten rock and gas spiraling into orbit around what remained of Earth. Over time, maybe days, maybe centuries, it's hard to say, that debris began to coalesce. Gravity pulled it together piece by piece, droplet by droplet, until it formed a glowing sphere, our moon. In a sense, the moon is made of Earth, scattered and reformed, a child of catastrophe. It carries within its rocks the memory of that ancient violence, the day our world nearly ended and instead gained a companion. There's something almost beautiful about that origin story, isn't there? That the moon, this gentle light in our night sky, this symbol of peace and romance and quiet, was born from cosmic disaster, from the worst day in Earth's history, its endings and beginnings tangled together. The moon's gravity is only about 1/6 of Earth's gravity. If you could somehow stand on the moon, and 12 people have, though the last did so over 50 years ago, one of the first things you'd notice is how light you feel. Not weightless, like floating in space, but buoyant, like you're underwater but without the water. Every step would be a small leap. Every motion would feel effortless, almost playful. The moon's gravity is only about 1/6 as strong as Earth's. That means if you weigh 180 pounds here, you'd weigh 30 pounds there. Your muscles, used to fighting Earth's pull, would suddenly be vastly overpowered for the job. The Apollo astronauts discovered this the hard way, or the fun way, depending on how you look at it. Even in their bulky spacesuits, Deus Ex, which weighed over 180 pounds on Earth, they could hop around like children, bounding across the lunar surface in strange, slow-motion leaps. But low gravity has its downsides too. It's why the moon couldn't hold onto an atmosphere if it had one. Gas molecules would simply drift away into space, too light for the moon's weak gravity to hold on to. It's why there's no weather, no wind, no rain. Just silence and stillness, broken only by the occasional meteor strike. There is no atmosphere on the moon, which means no weather, no wind, and no sound. Silence. True silence. The kind we never experience on Earth. No wind rustling through trees, no distant traffic hum, no birds, no breathing from the person next to you. On the moon, there's nothing to carry sound. No air molecules to vibrate and transmit waves. You could stand next to someone and shout and they wouldn't hear you. The only sound would be the vibrations travelling through the ground, through your spacesuit, into your bones. Without an atmosphere, there's no weather either. No clouds drifting by, no rain, no snow, no fog. The sky is always black, even during the lunar day, because there's no air to scatter sunlight and make it blue. The sun is just a blazing disk in the darkness, harsh and unfiltered. Stars are visible even at noon. And without wind or rain or any kind of erosion, things don't change. Not quickly, anyway. The footprints left by Neil Armstrong in 1969 are still there, pressed into the dust as crisp and clear as the day he made them. They'll remain for millions of years, maybe hundreds of millions, until micrometeorites slowly, grain by grain, erase them. It's a kind of immortality, I suppose, a mark left on a world that doesn't forget. The moon's surface temperature swings wildly from 260 degrees Fahrenheit in sunlight to minus 280 degrees Fahrenheit in shadow. Temperature on the moon is extreme. That's the word for it. During the lunar day, when the sun beats down on the surface for 2 weeks straight, temperatures soar to 260 degrees Fahrenheit. Hot enough to boil water, if there was any water. Hot enough to cook you if you weren't in a spacesuit. But step into shadow and everything changes. Without an atmosphere to trap and distribute heat, the temperature plummets to 280 degrees below zero. Colder than Antarctica in winter, colder than dry ice, cold enough to freeze carbon dioxide solid, if there was any. This is what happens when you have no air. On Earth, our atmosphere acts like a blanket, holding in warmth when the sun sets, preventing the kind of wild swings the moon experiences. But the moon is naked to space, exposed. Every sunrise is a furnace, every sunset a deep freeze. The Apollo astronauts had to carefully manage their suits' thermal systems to deal with these extremes, constantly adjusting to stay alive in a place that swings between oven and icebox. The moon is covered in a fine powder called regolith, created by billions of years of meteor impacts. The ground beneath the Apollo astronauts' feet wasn't like Earth soil. It was something else entirely. Regolith, a fine, powdery substance created by billions of years of meteor bombardment. every impact, from massive asteroid strikes to tiny micrometeorite collisions, pulverized the moon's surface, grinding rock into dust. This dust is strange stuff, and it's incredibly fine, almost like talcum powder, but with sharp, jagged edges because there's no wind or water to smooth them. It clings to everything through static electricity: boots, suits, equipment, tools. The Apollo astronauts found it maddeningly persistent. It got into every crevice, every joint, every seal. They brought it back into their lunar module on their suits, and it filled the cabin with a smell like spent gunpowder, acrid and metallic. But here's the remarkable thing. This dust holds history. Every grain is a record of impacts, of solar wind bombardment, of chemical reactions driven by radiation. Scientists can analyze lunar regolith and read in it the story of the solar system's past written in atoms and isotopes. The ground itself is a library if you know how to read it. The dark patches visible on the moon are ancient lava flows called Maria, Latin for seas. When you look up at the full moon, you can see patterns, dark patches against brighter grey, forming shapes that people throughout history have interpreted as faces, rabbits, figures. Early astronomers called these dark regions Maria, the Latin word for seas, because they thought they might be actual bodies of water. They weren't, of course. They're ancient lava flows frozen in time, remnants of an era when the moon was geologically active. Billions of years ago, massive asteroid impact cracked the moon's crust, and molten rock welled up from below, flooding vast basins and creating these dark, smooth plains. The lava cooled and solidified, leaving behind what we now call the lunar Maria, Mare Imbrium, Mare Serenitatis, Mare Tranquillitatis, thus poetic names for ancient stone. These Maria are actually darker than the surrounding highlands because they contain different minerals, richer in iron and titanium. They reflect less light, creating the contrast we see. And though the name seas was wrong, there's something almost fitting about it. These regions are smooth, relatively flat, calm compared to the heavily cratered highlands. If the moon ever had oceans, you could imagine them here, filling these vast basins. But it never did. The Maria are seas in name only, dry and dead, monuments to a volcanic past that ended over 1 billion years ago. The moon has over 300,000 craters larger than half a mile in diameter. The moon's surface is scarred. Everywhere you look, craters upon craters upon craters, overlapping, intersecting, some small as potholes, others vast as small countries. And scientists estimate there are over 300,000 craters larger than half a mile across. Count the smaller ones, the ones you'd need a microscope to see, and the number becomes essentially infinite. Each crater tells a story of violence, of something falling from the sky at tremendous speed and exploding on impact. Some of these impacts happened billions of years ago, when the solar system was young and chaotic, full of debris left over from planet formation. Others are more recent, geologically speaking, mere millions of years old, and new ones form even now, though rarely, when asteroids or comets find their way to the moon's surface. On Earth, we have craters too, but weather and plate tectonics erase them. Rain fills them in, wind smooths them out, vegetation covers them, continents shift and bury them. The moon has no such mechanisms, that every impact is preserved, a permanent record stretching back to the beginning. Walking on the moon, if you could walk freely without a spacesuit, without the need for oxygen, would be like walking through a museum of cosmic history. where every footstep lands on something ancient and violent and unrepeatable. The largest crater on the Moon is the South Pole Aitken Basin, stretching 1,550 miles across. The South Pole Aitken Basin is difficult to comprehend. 1,550 miles across. That's roughly the distance from New York to Denver, or London to Athens. A scar so enormous that you could fit several smaller countries inside it, with room left over. This crater formed around 4 billion years ago when something massive, an asteroid perhaps, or a small planet, slammed into the Moon's south polar region. The impact was so violent it punched through the crust and exposed the Moon's mantle, the layer beneath. Even now, billions of years later, this basin is one of the deepest, oldest structures on the lunar surface, reaching down over 8 miles below the surrounding terrain. You can see it from Earth with a good telescope, though you have to know where to look. It's on the far side, the hidden hemisphere, so it only becomes visible during periods of libration when the Moon's wobble gives us a peek around the edge. Standing at the center of this basin, if you could stand there, the walls would be beyond the horizon in every direction. You'd be in the middle of something so vast it would feel less like a crater and more like an entire landscape, a geography shaped by a single moment of cosmic catastrophe. A total solar eclipse is only possible because the Moon appears almost exactly the same size as the Sun in our sky. Here's a cosmic coincidence that feels almost too perfect to be random. The Moon and the Sun appear nearly the same size in Earth's sky. The Sun is 400 times larger than the Moon, but it's also 400 times farther away, and these ratios cancel out almost exactly. The result is that during a total solar eclipse, the Moon fits over the Sun like a lid on a jar, blocking it completely, revealing the Sun's corona in a moment of eerie, perfect alignment. This wasn't always true, and it won't always be true. The Moon used to be closer, which means it appeared larger and solar eclipses lasted longer. In the distant past, when dinosaurs looked up at the sky, if they thought to look, they saw a bigger Moon than we do. And in the future, as the Moon continues to drift away, it will appear smaller. Eventually it won't be able to completely cover the Sun during an eclipse. We'll get only annular eclipses, where a ring of sunlight remains visible around the Moon's edge. We live in a narrow window of time when total solar eclipses are possible, when the geometry works out just right. It's pure chance, as far as we know. The universe didn't arrange this for us. But standing in the path of totality, watching the Moon slide perfectly over the Sun, it's hard not to feel like we're witnessing something intentional, something meant to be. The Moon causes Earth's tides by pulling on our oceans with its gravity. The tides rise and fall twice a day in most places, pulled by the Moon's gravity like a gentle, invisible hand reaching across space. It's a phenomenon so familiar we barely think about it. High tide, low tide, the rhythm of the sea. But stop and consider what's actually happening. A world 250,000 miles away is moving our oceans, billions of tons of water, through nothing but gravitational traction. The Moon pulls harder on the side of Earth facing it than on the far side, creating a bulge of water on both sides of the planet. As Earth rotates beneath these bulges, coastlines move in and out of them, experiencing high and low tides. The Sun contributes too, which is why tides are higher during full and new moons when the Sun and Moon align. Spring tides, they're called. And lower when the Sun and Moon are at right angles, neap tides. Without the Moon, our tides would be much smaller, driven only by the Sun's weaker influence. The intertidal zones, those rich, or complex ecosystems where land meets sea would be different, smaller, less dynamic. Some scientists think life might have first ventured onto land in these tidal zones, adapting to the rhythm of wet and dry. If that's true, then the moon didn't just pull our oceans. It may have pulled life itself out of the water, setting the stage for everything that followed, including us. The moon's gravitational pull has been slowing Earth's rotation over time. Time itself is slowing down, not in any way you'd notice, not even close, but measurably, scientifically, the Earth's rotation is gradually decreasing, and the moon is responsible. Every day is getting longer by about 1.7 milliseconds per century. It doesn't sound like much, and in a human lifetime it isn't. But multiply that out over millions of years, over hundreds of millions, and the effect becomes dramatic. When dinosaurs walked the Earth, a day was only about 23 hours long. Go back to the very beginning, when the moon first formed and was much closer to Earth, and a day might have been only 5 or 6 hours. This happens because of tidal friction. The moon pulls on Earth's oceans, creating tidal bulges, and Earth's rotation tries to drag those bulges forward. But the moon's gravity pulls them back, creating friction that gradually slows Earth's spin. The energy doesn't disappear, it gets transferred to the moon, which uses it to move into a higher orbit. So as Earth spins slower, the moon drifts farther away. It's a slow exchange, a cosmic dance of energy and momentum, playing out over billions of years. Only 12 humans have ever walked on the moon, all between 1969 and 1972. 12 people. In the entire history of humanity, only 12 individuals have stood on another world. Neil Armstrong, Buzz Aldrin, Pete Conrad, Alan Bean, Alan Shepard, Edgar Mitchell, David Scott, James Irwin, John Young, Charles Duke, Eugene Cernan, Harrison Schmitt. All of them went between 1969 and 1972 during the Apollo program, and then we stopped. It's been over 50 years since the last moonwalk. 50 years since Eugene Cernan left the final boot print and climbed back into the lunar module, since he spoke the last words from the lunar surface. We leave as we came, and God willing, as we shall return, with peace and hope for all mankind. We haven't returned, not yet. There are people alive today who remember watching those missions on television, who saw the grainy footage of Armstrong descending the ladder, who heard his famous first words, and there are people born after 1972 who have never known a world where humans actively explored the moon. The missions have become history, then nostalgia, then something almost mythical. But the moon remains, patient as always, marked with 12 sets of footprints slowly fading under the rain of micrometeorites, waiting for the next visitor, whenever that might be. The moon rings like a bell when struck by meteorites, vibrating for hours afterward. When the Apollo missions left seismometers on the moon, they discovered something strange. The moon rings. Not in any way you could hear, obviously. There's no air to carry sound. But when meteorites strike the surface, or when astronauts deliberately crashed spent rocket stages into it, the moon vibrates, and those vibrations continue for hours. Thus, sometimes over an hour, far longer than similar impacts would cause on Earth. On Earth, seismic waves from an earthquake or impact die out quickly, absorbed by our planet's layers of molten and semi-molten rock. But the moon appears to be different. It has a rigid outer structure, possibly a thick solid shell surrounding a partially molten core. When struck, it resonates like a bell, the vibrations bouncing around inside with nowhere to dissipate. Scientists are still trying to fully understand what this means for the moon's internal structure. But there's something eerie about it, isn't there? This dead, silent world that rings when struck, humming to itself in frequencies no ear can detect. A sound that exists only as numbers on a graph, a vibration in stone. There's water ice hidden in permanently shadowed craters near the moon's poles. For most of human history, we thought the moon was bone dry, a desert world, utterly devoid of water. And for the most part, that's true. But in recent decades, we've discovered something unexpected. Ice. Not flowing water, not even exposed ice on the surface, but frozen water trapped in the coldest, darkest places on the moon. Permanently shadowed craters near the poles. These craters are strange places. Because of the moon's minimal axial tilt, sunlight never reaches their depths. They exist in eternal darkness, never warming above a few dozen degrees above absolute zero. Over billions of years, water molecules, delivered by comets perhaps, or created by chemical reactions when solar wind hits the surface, have migrated into these cold traps and frozen solid. How much ice is there? We're not entirely sure yet. Could be millions of tons, could be more. It's difficult to measure precisely because it's mixed with lunar soil, hidden, inaccessible. But if future lunar explorers ever establish a base near the poles, this ice could be invaluable. Water for drinking, oxygen for breathing, hydrogen for fuel, all extracted from frozen deposits that have sat undisturbed in darkness for longer than complex life has existed on Earth. The moon has moonquakes, though they're much weaker and less frequent than earthquakes. The moon isn't entirely still. It has quakes, small tremors that ripple through its interior, detectable only by sensitive instruments. The Apollo seismometers recorded thousands of these moonquakes over the years they operated, categorizing them into different types. And some moonquakes are shallow, occurring relatively close to the surface, and these can be surprisingly strong for a supposedly dead world, up to 5.5 on the Richter scale. Others are deep, originating hundreds of miles below the surface, and these occur with strange regularity, following a monthly pattern that corresponds to when the moon is closest to Earth. The stress of Earth's gravity, pulling and squeezing the moon as it orbits, apparently triggers these deep quakes. There are also thermal moonquakes, caused by the extreme temperature changes between the 2-week-long lunar day and the equally long lunar night. The surface expands and contracts, creaking and cracking like old wood. And then there are impact quakes caused by meteorites striking the surface, sending vibrations through the entire body of the moon. These quakes tell us the moon isn't quite as dead as it appears. There's still activity, still movement, still processes happening beneath that ancient cratered surface. Not life, not in any biological sense, but a kind of slow geological breathing, the moon settling into itself, adjusting to forces both internal and external. The moon's core is tiny compared to Earth's, making up only about 1 to 2% of its total mass. Deep inside the moon, at its very centre, there's a core of iron and nickel. But unlike Earth's massive core, which makes up about 1/3 of our planet's mass, the moon's core is tiny. It's only about 150 to 250 miles in radius, making up just 1 to 2% of the moon's total mass. This small core is one of the clues that led scientists to the giant impact theory. If the moon had formed independently, alongside Earth, or if it had been captured from elsewhere in the solar system, it would likely have a larger core. But if it formed from debris blasted off Earth's outer layers during the Theia collision, you'd expect it to be mostly made of lighter crustal and mantle material with very little iron, and that's exactly what we see. The Moon's core might still be partially molten, though this is debated. Seismic data from the Apollo missions suggest there could be a liquid outer core surrounding a solid inner core, similar to Earth's structure but on a much smaller scale. But without active missions on the surface, without seismometers currently operating, we're working with decades-old data, trying to piece together the Moon's interior from echoes and vibrations recorded in the 1970s. The Moon has no global magnetic field today. Though rocks show it once did billions of years ago, if you brought a compass to the Moon today it would spin uselessly, finding no north, no direction. The Moon has no global magnetic field, no invisible shield protecting it from the solar wind's constant bombardment. It's naked to space in a way Earth is not. But this wasn't always the case. When Apollo astronauts brought lunar rocks back to Earth, scientists discovered something unexpected. The rocks were magnetized. Not strongly, but detectably, as if they'd formed in the presence of a magnetic field. This means that billions of years ago the Moon had a magnetic field of its own, possibly generated by a dynamo effect in its molten core, similar to how Earth's field works today. What happened to shut it down? We're not entirely sure. Perhaps the Moon's core cooled and solidified, stopping the convection currents that created the field. Perhaps it was never very strong to begin with, and simply faded as the Moon's interior lost energy. Whatever the reason, the field disappeared, leaving the Moon exposed. Solar wind now strikes the surface directly, gradually altering its chemistry, darkening rocks over millions of years through a process called space weathering. The Moon bears the marks of this exposure, a world without protection, aging under the sun's relentless radiation. The term lunatic comes from the Latin word for moon, reflecting ancient beliefs that the Moon affected mental health. The word lunatic shares its root with lunar. Both come from luna, the Latin name for the Moon. For centuries, people believed the Moon influenced human behaviour, particularly mental health. Full moons were thought to drive people mad, to increase crime, to disturb sleep, to cause all manner of psychological disturbances. There's no scientific evidence for this, of course. Studies have repeatedly found no correlation between lunar phases and hospital admissions, crime rates, psychiatric episodes, or any other measurable human behaviour. The Moon doesn't make us crazy, at least not in any literal sense, and yet the belief persists. Perhaps because the Moon is so visible, so present in our lives, that it feels like it must do something beyond just reflecting sunlight. Perhaps because humans have always looked for patterns, for connections, for meaning in the natural world, and the Moon's phases provide an easy calendar to anchor those patterns to. Or perhaps it's simply that the Moon has always been associated with the night, with darkness, with the time when inhibitions fade and the world becomes strange. The Moon didn't create that strangeness, but it witnessed it month after month, and somehow became entangled with it in our collective imagination. A blue moon has nothing to do with colour. It simply means the second full moon in a calendar month. The phrase, "once in a blue moon," suggests rarity, something that happens only occasionally, and that's accurate enough. A blue moon, defined as the second full moon occurring within a single calendar month, happens roughly every 2.5 years. Not impossibly rare, but uncommon enough to be notable. The name is somewhat misleading though. Blue moons aren't actually blue. They look the same as any other full moon. Pale grey, maybe slightly yellow or orange when near the horizon, but never blue. The term's origin is murky. It may have come from a misunderstanding of an older definition, or from the idea of something being blue meaning unusual or unexpected. On very rare occasions, the moon can actually appear bluish, but this has nothing to do with lunar phases. It happens when Earth's atmosphere contains particles of a specific size, usually from volcanic eruptions or large wildfires, that scatter red light while allowing blue wavelengths through. After the eruption of Krakatoa in 1883, for instance, the moon appeared distinctly blue for nearly 2 years, but these are different phenomena entirely, connected only by coincidence of colour. The moon appears larger on the horizon than overhead, but this is an optical illusion. Have you noticed that the moon looks enormous when it's rising or setting, and hanging low on the horizon like a massive disk, but smaller and more distant when it's high overhead? You're not imagining it. The effect is real. But it's not the moon that's changing. It's your perception. This is called the moon illusion, and despite centuries of study, we still don't completely understand why it happens. The moon is actually slightly closer when it's overhead. You're standing on the side of Earth nearest to it. But the difference is negligible, far too small to account for the perceived size change. One theory suggests it's about context. When the moon is on the horizon, your brain compares it to distant objects, trees, buildings, mountains, and perceives it as large. When it's overhead, there's nothing to compare it to, just empty sky, and your brain interprets it as smaller. Another theory involves the way we perceive the sky itself, as if it were a flattened dome rather than a true hemisphere, making horizon objects seem farther away and therefore larger. Whatever the explanation, the illusion is powerful and universal. Humans across all cultures report experiencing it. You can test it yourself. Take a photograph of the moon on the horizon and then overhead. Measure them. They'll be the same size, pixel for pixel, but look with your naked eyes, and one will seem enormous, the other small. The mind playing tricks, creating meaning from geometry. Lunar eclipses can only occur during a full moon when Earth passes between the sun and moon. A lunar eclipse is Earth's shadow falling on the moon. It's a rare alignment, sun, Earth, or a moon in a perfect line, and it can only happen during a full moon when the moon is on the opposite side of Earth from the sun. But we don't get eclipses every full moon because the moon's orbit is tilted about 5 degrees relative to Earth's orbit around the sun. Most months the moon passes above or below Earth's shadow, missing it entirely. But when the alignment does work out, when the geometry is just right, Earth's shadow creeps across the moon's face, darkening it bit by bit. And here's where something strange happens. The moon doesn't disappear. Instead, it turns a deep, coppery red, glowing faintly in the darkness. This happens because Earth's atmosphere bends sunlight around the edges of our planet. The atmosphere filters out blue wavelengths and allows red light through, projecting it onto the moon's surface. In a sense, during a total lunar eclipse, the moon is illuminated by all of Earth's sunrises and sunsets simultaneously, painted red by the combined light of every dawn and dusk happening around our planet at that moment. It's a beautiful thought, isn't it? The moon bathed in our twilight, a reflection of a reflection, light that's travelled through our atmosphere before reaching it. The moon's orbit is not a perfect circle. It's an ellipse, bringing it closer and farther from Earth each month. The moon doesn't orbit Earth in a perfect circle. Its path is elliptical, an oval that brings it closer and then farther away with each monthly cycle. At its closest approach, called perigee, the Moon is about 226,000 miles from Earth. At its farthest, apogee, it's about 251,000 miles away. That's a difference of 25,000 miles. Yeah, enough to make the Moon appear noticeably larger and brighter at perigee than at apogee. When a full moon coincides with perigee, we get what's popularly called a supermoon. The Moon can appear up to 14% larger and 30% brighter than when it's at apogee. The difference is subtle. You might not notice unless you're comparing photographs, but it's real, measurable, a consequence of orbital mechanics. Ancient astronomers noticed this variation, this speeding up and slowing down as the Moon moved through its orbit. It was one of the many irregularities that made predicting the Moon's position difficult, one of the puzzles that eventually led to our understanding of gravitational physics. Kepler used observations of the Moon's motion to help formulate his laws of planetary motion. Yet Newton used those same irregularities to test his theory of gravitation. The Moon's imperfect orbit became a key to unlocking the mathematical laws governing all celestial motion. The Moon has a very faint atmosphere called an exosphere, so thin it's nearly a vacuum. When we say the Moon has no atmosphere, we're simplifying slightly. It does have an atmosphere, technically, an exosphere, the thinnest possible type of atmosphere, so tenuous it's barely distinguishable from the vacuum of space. This exosphere consists of isolated atoms and molecules, helium, argon, neon, sodium, potassium, even a bit of radon, drifting above the surface in such low concentrations that they rarely collide with each other. The total mass of the Moon's atmosphere is estimated to be around 25 tons. That sounds like a lot until you realise Earth's atmosphere weighs about 5 quadrillion tons. The Moon's entire atmosphere weighs less than a single large building. Where do these atoms come from? Some are delivered by solar wind, streams of charged particles from the sun that constantly bombard the Moon's surface. Some are knocked off surface rocks by micrometeorite impacts. Some, like radon, are released from radioactive decay of elements in the lunar soil, and some, like sodium, create a faint glow, a sodium tail that stretches behind the Moon as it orbits Earth, visible only with specialized instruments, a ghostly trace of atoms escaping into space. The far side of the Moon has a much thicker crust than the near side. The Moon is asymmetrical, not obviously so, you can't tell just by looking, but internally its structure is lopsided. The far side, the hemisphere we never see, has a crust that's about 30 miles thicker than the near side's crust. This asymmetry explains one of the Moon's most striking features, why the near side has so many dark maria, those ancient lava flows, while the far side has almost none. When massive impact struck the Moon billions of years ago, they needed to crack through the crust to allow lava to well up from below. On the near side, with its thinner crust, this was possible. The impacts broke through, and lava flooded the basins, creating the dark patches we see. But on the far side, the crust was too thick. The impacts couldn't break through completely, so the far side remains heavily cratered, its highlands largely intact, its surface bright and ancient. When spacecraft first photographed the far side in 1959, scientists were surprised by this difference. They expected the hidden hemisphere to look similar to the side we can see, but instead it was almost unrecognizable, a different world wearing the same skin. Why is the crust thicker on the far side? We're still not entirely certain. It may have to do with how the Moon formed, with material accumulating unevenly. Or it may be related to Earth's tidal effects during the Moon's early history, when it was much closer and rotating faster. The Moon keeps giving us mysteries, even as we solve old ones. The Moon is slowly stabilizing Earth's axial tilt, which gives us stable seasons. Earth tilts as it orbits the Sun, its axis inclined about 23.5 degrees from vertical. This tilt is why we have seasons. As Earth orbits, different hemispheres receive more or less direct sunlight, creating summer and winter, spring and fall. But that tilt isn't perfectly stable. Without the Moon, it would wobble chaotically over millions of years, swinging anywhere from 0 to 85 degrees. Imagine what that would mean for climate. An Earth with no tilt would have no seasons, just an eternal division between hot equator and frozen poles. An Earth tilted 85 degrees would experience extreme seasons, with each pole baking under months of continuous sunlight and then freezing in endless darkness. The climate would be wildly unstable, cycling through extremes, making the evolution of complex life difficult if not impossible. The Moon prevents this. Its gravitational influence acts like a stabilizer, damping out wobbles, keeping Earth's tilt relatively constant over time. There are still small variations. The tilt oscillates between about 22 and 24.5 degrees over a 41,000-year cycle, but these are gentle, predictable, manageable. The Moon gives us stable seasons, and stable seasons may have given us the conditions necessary for life to flourish. In a way, we owe our existence to the Moon, not just because it creates tides or lights the night, but because it steadies our world, keeps it from tumbling into chaos. A silent guardian, working through nothing but gravity, holding Earth's axis nearly constant for billions of years. The brightest spots on the Moon are young craters with fresh, reflective material exposed. When you look at the full Moon, some craters stand out brilliantly, brighter than their surroundings, with rays of white material streaking outward like frozen explosions. Called these are young craters, geologically young anyway, formed within the last few 100 million years. When a meteor strikes the Moon at high speed, it excavates material from beneath the surface, throwing it outward in all directions. This freshly exposed material is bright and reflective, not yet darkened by space weathering. Over time, solar wind and micrometeorite bombardment will gradually darken these rays, turning them grey like the surrounding terrain, but for now, they shine. The crater Tycho is one of the most prominent examples. It's about 53 miles across, with rays extending over 900 miles across the lunar surface, visible even to the naked eye during full moon. Tycho formed around 108 million years ago, recent enough that dinosaurs were still roaming Earth when the impact occurred. When you see those bright rays, you're seeing the aftermath of a cosmic collision that happened while T-Rex was hunting, while the continents were still drifting into their current positions. These bright craters are time markers, geological events dated by the fading of their rays. The older the crater, the fainter the rays, until eventually they disappear entirely, blending into the background. The Moon's face is a palimpsest, layers of impacts written and rewritten, but never quite erased, the newest ones shining brightest. The Moon's umbra, darker shadow, barely reaches Earth during solar eclipses, creating a narrow path of totality. When the Moon passes directly between Earth and the Sun during a solar eclipse, it casts a shadow, two shadows actually. The outer shadow, called the penumbra, is a region of partial darkness where the Sun is only partially blocked, but the inner shadow, the umbra, is a cone of total darkness where the Sun is completely hidden. and this umbra barely reaches Earth's surface. The path of totality, where observers experience a total solar eclipse, is typically only about 70 miles wide, sometimes narrower, sometimes slightly wider, but never very broad. Stand just outside this path and you'll see a partial eclipse, impressive but not transformative. Step inside the path and the sky goes dark, stars appear, the temperature drops and the sun's corona blazes into visibility around the moon's silhouette. This narrow path sweeps across Earth's surface as the moon's shadow races along at over 1,000 miles per hour. Totality at any given location lasts only a few minutes at most, sometimes just seconds, and then it's over, the shadow moving on, leaving observers blinking in returned sunlight. Eclipse chasers travel the world to stand in these narrow paths, to experience those brief minutes of totality. It's a peculiar kind of pilgrimage, driven by geometry and timing, following the moon's shadow as it traces its path across continents and oceans. Some people have witnessed dozens of total eclipses. Others spend a lifetime hoping to see just one. Ancient volcanic glass beads, formed from lunar fire fountains, have been found on the moon. Hidden in the lunar soil are tiny glass beads, some orange, some green, no bigger than grains of sand. They look almost like coloured sugar, sweet and translucent, but they're actually droplets of volcanic glass. Frozen in mid-flight billions of years ago, these beads formed during volcanic eruptions unlike anything Earth experiences today. Yet when ancient volcanoes on the moon erupted, they sometimes created fire fountains, jets of molten rock and gas shooting high into the airless sky. Without an atmosphere to slow them down, these droplets of lava travelled in perfect parabolic arcs, cooling and solidifying into glass as they flew, then raining back down to the surface. Apollo 17 astronaut Harrison Schmitt, the only geologist to walk on the moon, found deposits of orange glass beads at a site called Shorty Crater. The discovery was unexpected and exciting, evidence of explosive volcanic activity that scientists hadn't anticipated. These tiny beads contain trapped gases and trace elements that tell us about the moon's interior composition and volcanic history. Imagine standing on the moon billions of years ago, watching one of these fire fountains erupt. No sound, just a silent geyser of molten rock arcing into the black sky, glowing orange and red, raining glass across the landscape. The moon wasn't always quiet. It had its moments of violence, of beauty even, in its own alien way. The moon has extremely weak gravity, but it's still enough to hold orbit around Earth for billions of years. The moon's gravity is weak, only 1/6 of Earth's, but it's not nothing. It's enough to hold the lunar soil in place, to keep rocks from drifting away, to create subtle variations in spacecraft orbits. And it's enough, when combined with the moon's velocity, to keep it locked in orbit around Earth. Orbiting is a delicate balance. Too slow, and gravity pulls you down. Too fast, and you escape. The moon travels at about 2,288 miles per hour relative to Earth. Fast enough that if Earth suddenly disappeared, yet the moon would sail off into space in a straight line. But Earth is there, pulling the moon toward it, curving that straight line into an ellipse. This balance has held for 4.5 billion years, through ice ages and warm periods, through asteroid impacts and volcanic eruptions, through the entire evolution of life on Earth. The moon has circled our planet without fail. It's slowing down slightly, drifting outward, but the fundamental relationship remains. Earth and moon, locked together by gravity, partners in a dance that will continue until the sun expands and consumes them both. Sunrise on the moon lasts for several Earth days as the sun slowly climbs above the horizon. On Earth, sunrise is quick. The sun appears on the horizon, and within minutes it's fully risen, the day begun. But on the moon, sunrises are slow, almost surreal experience stretched out over several of our days. This happens because the moon rotates so slowly. A full day-night cycle on the moon, from sunrise to sunrise, takes about 29.5 Earth days. That means the sun creeps across the sky at a glacial pace, taking roughly 2 Earth weeks to move from horizon to horizon. Imagine watching a lunar sunrise. The sun appears as a brilliant point on the horizon, so bright it would hurt to look at directly. But it doesn't leap upward. It inches, slowly, almost imperceptibly, the shadows around you gradually shortening as hours pass. After an Earth day, the sun is still low, still casting long shadows. After 2 days, it's climbed higher, but still far from overhead. It takes the better part of a week for the sun to reach its highest point in the lunar sky. And then the process reverses, and sunset lasts just as long, the sun taking days to descend to the horizon and finally disappear, plunging the landscape into a darkness that will last another 2 weeks. Time moves differently there, stretched and strange. A world where day and night are measured not in hours but in weeks. The moon has no plate tectonics. Its surface is geologically dead and has been for billions of years. Earth's surface is alive in a geological sense. Continents drift, mountains rise, ocean floors spread and subduct, volcanoes erupt, earthquakes reshape the land. This is plate tectonics, the slow churning of Earth's crust driven by heat from our planet's interior. It recycles rock, creates new landforms, erases old ones. Nothing on Earth's surface is truly permanent. The moon has none of this. Its crust is a single, solid shell, unbroken and unmoving. There are no tectonic plates, no drifting continents, no volcanic activity. The moon's interior is cooled and largely solidified, no longer able to drive the kind of geological processes that keep Earth dynamic. This means the moon's surface is ancient and unchanging. The craters we see formed billions of years ago and remain almost exactly as they were. The Maria, those ancient lava flows, haven't been subducted or eroded or covered by new geological activity. They just sit there, frozen in time, a record of the moon's past preserved in perfect stillness. In a way, the moon is a museum, a place where history accumulates rather than being recycled. Every impact, every lava flow, every geological event is written on the surface and stays written, fading only imperceptibly under the slow rain of micrometeorites and the patient weathering of solar wind. It's a different kind of world than ours, one where the past is never truly buried. Some lunar craters are so deep that their floors remain in perpetual darkness, creating natural cold traps. Near the moon's poles there are craters whose floors have never seen sunlight. Not in millions of years, possibly not in billions. These are the permanently shadowed regions, places where the geometry of the moon's tilt and the high walls of the craters conspire to keep the depths forever dark. Without sunlight, these crater floors are extraordinarily cold, some of the coldest naturally occurring places in the solar system. Temperatures plunge to around negative 400 degrees Fahrenheit, colder than Pluto's surface, like cold enough to freeze almost anything solid. These cold traps act as natural freezers, capturing and holding volatile materials that would otherwise evaporate. water molecules delivered by comets or created by chemical reactions on the surface migrate into these dark craters and freeze, accumulating over billions of years. Possibly other volatiles too, carbon dioxide, ammonia, methane, organic compounds, all preserved in eternal darkness and cold. Future lunar explorers might visit these craters, descending into darkness with lights and drills, mining ancient ice from the shadowed depths. It's a strange thought, extracting water from a place that hasn't felt warmth since before complex life emerged on Earth, bringing light to corners of the moon that have been dark since the beginning. The moon's soil contains oxygen locked in minerals, potentially enough to support future human colonies. The moon looks barren and lifeless, and in a biological sense it is. But it's not quite as resource-poor as it might seem. The lunar soil, that fine grey dust covering the surface, contains oxygen. Lots of it, actually. Not as breathable air, but chemically bound in minerals, particularly in compounds like silicon dioxide and various metal oxides. By weight, the moon's regolith is about 40 to 45% oxygen. That's a tremendous amount. Enough that if we could extract it, we could potentially support human colonies without having to ship oxygen from Earth. The challenge is extraction. Breaking those chemical bonds requires energy and sophisticated equipment. But it's technically possible, and several proposed methods exist for liberating oxygen from lunar soil. Imagine a future lunar base with oxygen generators pulling breathable air directly from the ground beneath them. It would be a strange kind of self-sufficiency, turning rock into atmosphere, transforming the moon's own substance into life support. The moon providing for its visitors, in its own way, through chemistry and engineering. Astronauts reported that lunar dust smells like spent gunpowder when brought inside their spacecraft. One of the more unexpected discoveries from the Apollo missions came not from scientific instruments, but from the astronauts' noses. When they returned to the lunar module after moonwalks, still covered in fine lunar dust, they noticed a smell, acrid, sharp, metallic. Many compared it to spent gunpowder, others to burnt charcoal or the air after fireworks. This was puzzling because the dust itself, exposed to vacuum on the surface, has no smell. Smell requires volatile molecules, and in vacuum any volatiles would have long since evaporated. So where was the smell coming from? The leading theory is that it's a chemical reaction. Lunar dust is constantly bombarded by solar wind, which oxidizes its surface. When this oxidized dust is brought into the oxygen-rich environment of the spacecraft cabin, chemical reactions occur, releasing volatile compounds that our noses detect. In a sense, the dust wasn't smelling like gunpowder. It was actively reacting with the air, creating new compounds we could smell. It's a small detail, a sensory note in the margins of history. But it reminds us that space exploration is a physical embodied experience. The moon has a smell, at least when it meets oxygen for the first time in billions of years. A smell no one expected, recorded in mission transcripts and astronaut memoirs, a strange footnote in the story of our visits to another world. The moon has mascons, concentrations of dense material beneath Maria that create gravity anomalies. Beneath some of the moon's Maria, hidden from view but detectable by spacecraft, are mascons, mass concentrations, regions where material is denser than surrounding areas, creating local increases in gravity. These mascons were discovered accidentally when early lunar orbiters experienced unexpected changes in their trajectories. Spacecraft flying over Maria would speed up slightly as the extra gravity pulled them forward, then slow down as they passed beyond the Mascons' influence. The effect is small but measurable, and it was a surprise to mission controllers who hadn't anticipated it. What causes Mascons? The leading theory is that they're remnants of the massive impacts that created the Maria Basins. When an asteroid or comet slammed into the moon, it excavated a deep hole and possibly punched through the crust into the denser mantle below. Later, when lava flooded the basin, it filled in the depression with heavy basaltic rock. The result is a region where material is denser than average, creating a gravitational anomaly. These hidden masses affect spacecraft orbits and tell us about the moon's internal structure. They're invisible clues written in gravity, revealing layers and densities that we can't see but can detect through their influence on motion and trajectory. Chinese mythology tells of Chang'e, a goddess who lives on the moon, inspiring the name of China's lunar missions. Throughout history, cultures around the world have populated the moon with stories, gods, and legends. In Chinese mythology, the moon is home to Chang'e, a goddess who drank an elixir of immortality and floated to the lunar surface, where she lives in a palace with only a rabbit for company. The rabbit, the jade rabbit or Yutu, is said to pound herbs with a mortar and pestle, preparing the elixir of life. If you look at the full moon and use your imagination, you can see the shape of a rabbit in the dark Maria, its long ears, its crouched body. Different cultures see different things in those shadows. A man's face in Western tradition, a rabbit in Chinese folklore, a woman in some indigenous American stories. When China began its lunar exploration program, it named its missions Chang'e, honoring this ancient connection between the moon and mythology. The first rover they landed on the moon was named Yutu, the Jade Rabbit. It's a poetic gesture, linking modern space exploration to stories told for thousands of years, suggesting that even in an age of science and technology, we still feel the pull of those old narratives, still see the moon as a place of wonder and myth. The moon's escape velocity is only 5,300 miles per hour, compared to Earth's 25,000 miles per hour. To leave Earth, to break free of our planet's gravitational grip and venture into space, a rocket must reach a speed of about 25,000 miles per hour. That's escape velocity, the minimum speed needed to overcome gravity without any additional propulsion. It's a tremendous speed, requiring massive rockets and enormous amounts of fuel. But on the moon, escape velocity is only about 5,300 miles per hour, less than a quarter of what's needed on Earth. This makes the moon an ideal launching point for deeper space missions. A rocket departing from the lunar surface needs far less fuel than one launching from Earth, which means it can carry more payload, travel farther, accomplish more. This is why some space planners envision the moon as humanity's gateway to the solar system. Build infrastructure there, fuel production facilities, launch platforms, habitats, and suddenly Mars, the asteroid belt, even the outer planets become more accessible. The moon could become a cosmic service station, a place where spacecraft refuel and resupply before heading outward. It's a reversal of perspective. For most of history, we've thought of the moon as a destination, a place to reach. But perhaps it's better understood as a departure point, a stepping stone. Not the end of the journey, but the beginning of the next one. Mare Tranquillitatis, the Sea of Tranquility, was chosen as humanity's first lunar landing site for its smooth, flat terrain. When NASA began planning the first moon landing, they needed a site that was relatively safe, smooth enough that the lunar module could land without hitting boulders or tipping into a crater. flat enough that the astronauts could walk around and work without too much difficulty. They also wanted a site near the lunar equator where communication with Earth would be easier. They chose Mare Tranquillitatis, the Sea of Tranquility, one of the dark lava plains visible from Earth. It met all the criteria: relatively flat, relatively smooth, free of obvious hazards. On July 20th, 1969, Neil Armstrong and Buzz Aldrin descended toward this ancient lava flow, Armstrong taking manual control in the final moments to avoid a boulder field, finally setting down with less than 30 seconds of fuel remaining. Tranquility Base here. The Eagle has landed. Those words mark the first time humans touched another world, and the location has remained significant. Mare Tranquillitatis is now a historical site, marked by the descent stage of the lunar module, still sitting where Armstrong and Aldrin left it, surrounded by footprints and equipment, and the American flag they planted. Proposals have been made to protect these artifacts, to preserve them as monuments to human achievement. The first steps on another world, frozen in place, waiting in tranquility. The moon's surface is covered in fine dust that levitates slightly above the ground during lunar sunrise and sunset. Here's something strange. During lunar sunrise and sunset, dust on the moon's surface begins to levitate. Not dramatically, we're talking about particles rising just inches or feet above the ground, but measurably, detectably, creating a faint haze along the terminator, the boundary between day and night. This happens because of static electricity. Solar wind, streams of charged particles from the sun, constantly bombards the moon's surface, building up electrical charges on dust grains. During sunrise and sunset, when the terminator passes over a region, the transition from darkness to light creates electric field changes. Dust particles charged positively on the sunlit side and negatively in shadow repel each other and lift off the surface. Astronauts on later Apollo missions reported seeing a glow on the horizon before sunrise, a faint brightening caused by sunlight scattering off this levitating dust. It's called horizon glow, and it's a uniquely lunar phenomenon. On Earth, dust settles. On the Moon, in the absence of air and in the presence of solar wind, dust dances, hovering above the surface in ghostly clouds too thin to see directly, but bright enough to catch the light. There are massive underground lava tubes on the Moon that could house entire cities. Beneath the Moon's surface, hidden from view, are enormous hollow tunnels carved by ancient lava flows. These lava tubes form the same way they do on Earth. Lava flowing downhill creates a crust on its surface, while continuing to flow beneath, and when the eruption stops, the lava drains away, leaving behind a hollow tube. But lunar lava tubes are much larger than Earth's because of the Moon's lower gravity. On Earth, lava tubes rarely exceed 50 feet in diameter before their roofs collapse. On the Moon, they can be hundreds of feet wide, possibly even larger. Some estimates suggest tubes up to a mile in diameter might exist, though this remains unconfirmed. These tubes would make ideal locations for future lunar bases. They provide natural protection from radiation, which is a major challenge on the airless lunar surface. They're shielded from temperature extremes and from micrometeorite impacts. A base built inside a lava tube could potentially house thousands of people, an underground city protected by the Moon's own stone. Explorers would enter through skylights, places where the tube's roof has partially collapsed, descending into darkness with lights and equipment, discovering vast chambers that have been sealed and dark for billions of years. It's a frontier waiting beneath the frontier, hidden architecture created by geology, ready for habitation. The Moon has extremely low seismic activity compared to Earth, making it geologically quiet. Earth is restless. At any given moment, somewhere on our planet, the ground is shaking. Earthquakes ranging from imperceptible tremors to devastating quakes that topple buildings and reshape coastlines. This is the cost of being geologically active, of having plate tectonics and a molten interior constantly in motion. The Moon, by contrast, is quiet. It has moonquakes, yes, but they're rare and weak compared to earthquakes. The Moon's interior is largely solid and cold, no longer driving the kind of activity that makes Earth so dynamic. Most moonquakes are tiny, barely detectable even by sensitive instruments. This geological stillness makes the Moon an ideal location for certain scientific instruments. Gravitational wave detectors, for instance, are extremely sensitive to vibration. On Earth, they have to filter out constant seismic noise, traffic, ocean waves, distant earthquakes, even people walking nearby. On the Moon, the background vibration is minimal, making it easier to detect the faint ripples in space-time that gravitational waves create. The same quiet makes the Moon attractive for radio telescopes. On Earth, we're surrounded by radio interference, cell phones, satellites, power lines, everything electronic. The far side of the Moon is the quietest place in the solar system from an electromagnetic perspective, shielded from Earth's radio chatter by the Moon's entire bulk. A radio telescope there could listen to the universe without distraction, hearing signals too faint to detect from Earth. Lunar rocks brought back by Apollo missions are between 3.2 and 4.5 billion years old. The rocks astronauts brought back from the Moon are ancient in a way that's difficult to grasp. The youngest lunar samples are about 3.2 billion years old, roughly the age of the oldest rocks we can find on Earth. The oldest are 4.5 billion years old, dating back to the Moon's formation, making them some of the oldest rocks in the solar system. This is because the Moon's surface doesn't recycle. On Earth, plate tectonics subduct old crust and bring up new material. Erosion wears down mountains and fills in valleys. The oldest rocks are rare, preserved only in special circumstances. But on the Moon, rocks just sit there, accumulating age, untouched by weather or tectonic activity. Scientists studying these lunar samples are looking at material that formed when the solar system was young, when planets were still being bombarded by debris left over from their formation. The rocks contain impact glass, formed when meteorites melted surface material. They contain volcanic minerals, frozen lava from eruptions that happened when Earth was still dominated by single-celled organisms. They contain cosmic ray tracks, damage from high-energy particles that have been hitting them for billions of years. Each sample is a time capsule, carrying information not just about the Moon, but about the early solar system, about conditions that existed before Earth had continents or oceans or life. We study them in laboratories, cutting them into thin sections, analysing their chemistry atom by atom, reading the stories written in their structure. The Moon's surface layer is so loosely packed that it acts as excellent insulation. Lunar regolith, that fine dust covering the surface, has an unusual property. It's an excellent insulator. The particles are loosely packed with lots of empty space between them, and in vacuum, with no air to conduct heat, this creates a material that resists temperature transfer remarkably well. What this means is that just a few feet below the Moon's scorching or freezing surface, the temperature becomes relatively stable. Even as the surface swings from 260 degrees Fahrenheit in sunlight to minus 280 degrees Fahrenheit in shadow, the subsurface stays around minus 4 degrees Fahrenheit year-round. It's still cold by human standards, but it's constant, predictable, manageable. This natural insulation is another advantage for future lunar bases. Bury your habitat a few feet underground, and you won't have to deal with the extreme temperature swings that make the surface so hostile. You could maintain comfortable temperatures with far less energy than would be needed for a surface structure. The Moon, in its own way, offers protection, not through atmosphere or magnetic fields, but through the simple physics of loose dust in vacuum. The Moon glows faintly even during lunar eclipses due to sunlight refracted through Earth's atmosphere. During a total lunar eclipse, when Earth's shadow completely covers the Moon, well, you might expect the Moon to disappear, to go completely dark, but it doesn't. Instead, it glows a deep coppery red, faintly visible against the night sky. This happens because Earth's atmosphere acts like a lens, bending sunlight around the edges of our planet. Blue wavelengths scatter away, the same scattering that makes our sky blue during the day, while red wavelengths pass through and onto the Moon's surface. Think about what this means. The light illuminating the Moon during an eclipse is sunlight that has passed through Earth's atmosphere, filtered through every sunset and sunrise happening around our planet at that moment. If you were standing on the Moon during a lunar eclipse and looked up, you'd see Earth as a black disk ringed with red light. All of Earth's twilight zones simultaneously visible as a burning halo. The exact colour of an eclipsed moon varies depending on Earth's atmospheric conditions. If there's been a major volcanic eruption recently, ash in the stratosphere can make the eclipse darker and redder. Clear atmospheric conditions create brighter, more orange eclipses. In a sense, a lunar eclipse is Earth showing the Moon what our atmosphere looks like, projecting our weather and geology onto our companion's face. The Moon's formation likely gave Earth its unusually large iron core. When Theia collided with early Earth, the impact was selective in what it vaporized and ejected. The collision happened at an oblique angle with tremendous energy, vaporizing primarily lighter materials, silicates, minerals from the crust and upper mantle. Heavier materials, particularly iron, were less affected. Most of Earth's iron and Theia's iron then sank to the center of the reformed Earth, creating our unusually large iron core. The Moon, meanwhile, formed primarily from the lighter materials that were vaporized and thrown into orbit. This is why the Moon has such a small iron core. Most of the iron stayed with Earth. It's also why the Moon's overall density is lower than Earth's, and why its chemical composition resembles Earth's mantle more than Earth as a whole. In a strange way, the Moon made Earth more iron-rich. The collision segregated materials, concentrating heavy elements in Earth and lighter elements in the Moon. This might have been crucial for Earth's habitability. Our large iron core generates Earth's magnetic field, which shields us from solar wind and helps protect our atmosphere. Without Theia's impact, without the formation of the Moon, Earth might have a smaller core, a weaker magnetic field, perhaps no protective magnetosphere at all. The Moon didn't just become Earth's companion, it reshaped our planet, altered its composition, possibly made it more suitable for life. A gift born from catastrophe. The Moon has swirls of magnetic material on its surface that deflect solar wind, creating bizarre patterns. Scattered across the Moon's surface are strange, bright swirls, sinuous patterns that look almost painted on, winding across the landscape in curves and loops. These aren't topographic features. You wouldn't see them if you were standing on the surface. They're albedo patterns, regions where the surface is brighter than its surroundings, visible only from above. What causes them? We're still not entirely sure. No, but they're associated with magnetic anomalies, localized regions where crustal rocks retain ancient magnetism. These magnetic fields are weak but strong enough to deflect solar wind particles, protecting the underlying rock from space weathering. Over millions of years, the protected areas remain brighter, while surrounding areas darken, creating these ghostly swirls. One theory suggests these magnetic anomalies formed from ancient impacts on the opposite side of the Moon. When a massive impact occurred, seismic waves travelled through the Moon's interior and converged at the antipodal point, the spot directly opposite the impact, creating intense heating and magnetic field generation. Another theory involves the remnants of the Moon's ancient global magnetic field, preserved in certain rocks like fossil magnetism. Whatever their origin, the swirls are beautiful and mysterious, patterns that seem almost intentional, as if the Moon is trying to tell us something in a language written in magnetism and light. The Moon's gravity creates a slight bulge in Earth's crust, not just in the oceans. We think of tides as an ocean phenomenon, water rising and falling along coastlines, harbours filling and emptying twice a day. But the Moon's gravity doesn't just pull on water, it pulls on everything. The oceans, yes, but also the solid ground beneath your feet. Earth's crust rises and falls by about 12 inches each day in response to the Moon's gravitational tug. 12 inches. The ground itself is tidal, bulging toward the Moon and away from it, flexing like a slow planetary heartbeat. You can't feel it happening. The motion is too gradual, too widespread, but it's real, measurable, constant. This crustal tide creates stress in the Earth's interior, generating a tiny amount of heat through friction. It's not much, not compared to the heat from radioactive decay or the residual warmth from Earth's formation, but it's there, another way the Moon influences our planet. Even the solid ground responds to the Moon's presence, rising to meet it and falling away over and over every day for billions of years. Imagine that. The Earth itself breathing in rhythm with the Moon's orbit, the entire crust flexing, mountains rising slightly higher and then settling back, valleys deepening and shallowing. It's invisible to us, imperceptible, but it's happening right now, beneath you, the ground moving in response to a world 250,000 miles away. 12 Apollo astronauts left behind commemorative plaques, flags, used as scientific instruments still on the Moon today. The Apollo missions left more than footprints. Scattered across 6 landing sites are the remnants of humanity's visits, descent stages from lunar modules, still resting where they landed. American flags, though likely bleached white by decades of unfiltered sunlight, commemorative plaques with messages to future visitors, discarded equipment, lunar rovers, cameras, tools, bags of waste, and scientific instruments. Some of the Apollo missions deployed experiments that operated for years after the astronauts left. Seismometers that detected moonquakes and meteor impacts. Laser retroreflectors, arrays of mirrors that reflect laser beams back to Earth, allowing scientists to measure the Moon's distance with incredible precision. These retroreflectors are still in use today, are still functioning perfectly after even 50 years, perhaps the most durable scientific instruments humanity has ever built. but everything up there is slowly degrading. The harsh environment, extreme temperature swings, unfiltered radiation, micrometeorite bombardment takes its toll. Plastics become brittle, metals corrode in strange ways, fabrics disintegrate. The flags are probably tattered now, if they haven't fallen over entirely. These artifacts are becoming ruins, the first archaeological sites beyond Earth. Someday, perhaps, they'll be preserved as historical monuments, protected and maintained. Or perhaps they'll simply continue to decay until they're indistinguishable from the lunar surface around them. Either way, they mark the places where we went, where we stood, where we briefly made another world our own. Lord, the moon experiences earthshine, light reflected from Earth that faintly illuminates its night side. When you see a crescent moon in the evening sky, look closely at the dark portion, the part that's not directly lit by the sun. Sometimes you can see it glowing faintly, a ghostly illumination filling in the rest of the circle. This is earthshine, light from the sun that's bounced off Earth, travelled to the moon, reflected off the lunar surface, and travelled back to your eyes. From the moon's perspective, Earth is enormous and bright, much brighter than the moon appears from Earth. When the moon is a thin crescent in our sky, from the moon's viewpoint, Earth is nearly full, blazing in the black sky like a blue and white marble. That earthshine is enough to dimly light the lunar landscape during what would otherwise be night. Leonardo da Vinci was one of the first to correctly explain this phenomenon, 5 centuries before we visited the moon. He understood that the moon shines only by reflected sunlight, and that Earth could do the same, illuminating the moon's night side. It was an insight that required thinking of Earth not as the centre of everything, but as just another world in space, reflecting light like any other. The moon's low gravity allows dust kicked up by meteor impacts to travel in perfect parabolic arcs. On Earth, when something explodes or impacts the ground, debris flies outward but is quickly slowed by air resistance. Dust clouds billow and spread, chunks of material tumble irregularly, affected by drag and wind. But on the moon, there's no air to slow anything down. When a meteor strikes the lunar surface, where it excavates material and throws it outward at high speed, each particle, from boulders to dust grains, follows a perfect parabolic trajectory. This same curve a thrown ball would follow in vacuum. Some particles land nearby, others travel for miles, all in graceful arcs determined purely by their initial velocity and the moon's gravity. This creates ray patterns around fresh craters, long streaks of ejected material radiating outward, sometimes extending hundreds of miles. The material doesn't spread or dissipate like it would on Earth. It just flies, following Newton's laws precisely, and lands wherever geometry dictates. If you could watch a meteor impact on the moon in slow motion, you'd see a beautiful, almost choreographed explosion. Material fountaining upward and outward in perfect parabolas, some particles reaching escape velocity and leaving the moon entirely, others arcing back down to create secondary craters where they land. It's physics in its purest form, unobscured by atmosphere or friction. The moon's south pole has areas that receive almost continuous sunlight, called peaks of eternal light. While some lunar craters are trapped in perpetual shadow, there are also places that experience the opposite, nearly continuous sunlight. These are the peaks of eternal light, mountain tops near the lunar poles that remain illuminated for most or all of the lunar year. These peaks exist because of the moon's minimal axial tilt. The moon's axis is tilted only about 1.5 degrees compared to Earth's 23.5 degree tilt. This means the sun never gets very high above the horizon at the poles, but it also means that elevated features can catch sunlight even when lower terrain is in shadow. For future lunar bases, these peaks would be ideal locations. Continuous sunlight means continuous solar power. No need for batteries to survive the 2-week lunar night. The locations are also relatively mild in temperature, never experiencing the extreme heat of the equatorial day or the extreme cold of polar craters. Imagine a solar array on one of these peaks, panels gleaming in eternal sunshine, generating power without interruption. Below, in the permanently shadowed craters, ice waits to be mined. The poles offer the best of both resources, energy and water, light and darkness side by side, separated by a few miles of lunar terrain. The moon wobbles slightly in its orbit, a phenomenon called libration that lets us see 59% of its surface over time. The moon is tidally locked, always showing us the same face. But that's not quite the whole story. Due to various orbital mechanics, the elliptical shape of the moon's orbit, its tilted axis, and the fact that it rotates at constant speed while its orbital velocity varies, the moon appears to rock back and forth and nod up and down as seen from Earth. This wobbling is called libration, and it allows us to peek around the edges. At different times during the lunar month, we can see a bit more of the eastern edge, or the western edge, or the northern or southern regions. Over time, these wobbles add up, allowing us to see 59% of the moon's surface from Earth, rather than just 50%. Let the remaining 41%, the true far side, remained completely hidden until spacecraft photographed it in 1959. It's strange to think that for all of human history until 60-some years ago, we simply didn't know what 41% of the moon's surface looked like. We could theorize, imagine, guess, but we couldn't see. Libration also means that from the moon, Earth doesn't hang perfectly still in the sky. It wobbles too, moving back and forth across about 15 degrees of arc. From some locations near the edge of the moon's near side, Earth would rise and set over the course of a month, spending half the time visible and half below the horizon. A lunar observer there would see Earth rise and Earth set, slow and stately, a dance between worlds. The moon's Maria formed when massive asteroid impacts cracked the crust, allowing lava to flood out. The Maria, those dark patches we see on the full moon, have a violent origin story. They started as impact basins, enormous craters created when asteroids tens or hundreds of miles across slammed into the moon during a period called the Late Heavy Bombardment, roughly 3.8 to 4 billion years ago. These impacts were so powerful they cracked the moon's crust, punching through to the mantle below. For millions of years after each impact, the basins remained empty, giant scars on the lunar surface. But the moon's interior was still hot, still geologically active, and eventually magma began welling up through the cracks. The lava flows were immense, flooding the basins to depths of hundreds or even thousands of feet, creating vast plains of solidified basalt. These flows happened over millions of years, with multiple eruptions filling and refilling the basins. Eventually the moon's interior cooled, volcanic activity ceased, and the Maria were left as we see them now, dark, smooth, ancient. It's a two-stage process, first destruction, then creation. The impacts nearly shattered the moon, but the subsequent lava flows healed those wounds, filling them with new rock, creating the patterns we see today. Violence followed by slow repair, catastrophe followed by centuries of geological patience. The moon has wrinkle ridges, long, sinuous formations created as ancient lava flows cooled and contracted. If you look closely at images of the Luna Maria, you'll see long, winding ridges snaking across the dark plains. Wrinkle ridges, geologists call them, or sometimes mare ridges. They look almost like frozen waves, or the wrinkles in a bedsheet pulled tight. These formed as the ancient lava flows cooled and contracted. As molten rock solidifies, it shrinks slightly, and on the scale of the Maria, plains hundreds of miles across, this shrinkage creates compression. The surface buckles and folds, creating ridges that can be dozens of miles long and hundreds of feet high. Some wrinkle ridges also formed as the basins themselves sank under the weight of the lava. The Maria are heavy, and over time they've caused the underlying crust to sag downward, creating more compression and more folding at the edges. These ridges are evidence of the moon's geological past, frozen snapshots of processes that happened billions of years ago. The lava that formed them cooled and solidified. The compression that shaped them ceased, and the ridges have remained unchanged ever since, waiting patiently for someone to notice them, to photograph them, to understand what they mean. The moon influences Earth's length of day much more than the sun does. Earth's rotation is gradually slowing, and while multiple factors contribute to this, the moon is by far the largest. The sun also exerts tidal forces on Earth, but because the moon is so much closer, even though it's much smaller, its effect is about twice as strong. This happens through tidal friction. The moon creates tidal bulges in Earth's oceans and crust. Earth's rotation tries to drag these bulges forward, but the moon's gravity pulls them back, creating a braking effect. Over millions of years, this has significantly slowed Earth's spin. 400 million years ago, during the Devonian period, a year had about 400 days. The days were shorter, only about 22 hours long. Go back further to the Precambrian, and days might have been as short as 18 hours. The moon has been gradually stealing rotational energy from Earth, using it to push itself into a higher orbit. Eventually, billions of years from now, Earth and Moon would reach a stable configuration where Earth's day equals the Moon's orbital period, about 47 current days. Earth would become tidally locked to the Moon, always showing it the same face just as the Moon is locked to Earth. But this won't happen before the Sun expands into a red giant and destroys both worlds. The Moon's surface is constantly being gardened by micrometeorite impacts, slowly mixing the soil. The lunar surface is never truly still. At any given moment somewhere on the Moon, a micrometeorite is striking, a tiny piece of space debris travelling at tens of thousands of miles per hour, vaporizing on impact and throwing up a small spray of dust. These impacts are constant and relentless. Every square meter of the Moon's surface is hit by micrometeorites every few years. Over millions of years, this bombardment churns the surface, mixing the soil, burying some materials and exposing others. Scientists call this process gardening. The lunar regolith is constantly being turned over, like soil in a garden, though the mechanism is impacts rather than ploughs. This gardening means the lunar surface is well mixed. Samples collected from just the top few inches contain materials from much deeper, brought up by ancient impacts. It also means that nothing stays on the surface indefinitely. Footprints, equipment, or artifacts, all are slowly being buried under micrometeorite debris, grain by grain, impact by impact. The process is slow, unimaginably slow by human standards. It might take millions of years to bury something under just a few inches of new material. But the moon has time. Endless time. And eventually even the Apollo landing sites will be covered, the footprints erased, the equipment buried, leaving no trace that we were ever there except perhaps the laser retroreflectors, still faithfully reflecting Earth's laser beams from beneath a thin layer of dust. The moon may have had a brief magnetic field that lasted only 100 to 200 million years. The moon once had a magnetic field. That much we know from magnetized rocks brought back by Apollo astronauts. But here's what's puzzling. This field seems to have existed for only a brief period in the moon's early history, perhaps 100 to 200 million years, and then it vanished. On Earth, our magnetic field has persisted for billions of years, generated by convection currents in our molten outer core. For the moon to generate a field, even temporarily, something unusual must have been happening in its small core. One theory suggests the moon's core underwent vigorous stirring early on, perhaps driven by gravitational interactions with Earth when the moon was much closer. Another theory proposes that the giant impact that formed the moon left the interior in a highly energetic state that gradually dissipated. Whatever created the field, it didn't last. The moon cooled, the core settled, and the magnetic dynamo shut down. Now the moon travels through space unprotected, its ancient magnetism preserved only as fossil records in certain rocks, ghostly traces of a shield that once existed and then disappeared, leaving the moon vulnerable to everything space could throw at it. The moon's gravitational influence helped slow Earth's rotation when days were much shorter. Imagine Earth in its youth, spinning wildly, days flashing by in just a few hours. Some models suggest that immediately after the moon formed, when it was much closer to Earth, a day might have lasted only 5 or 6 hours. The sky would have been a blur, sunrise, noon, sunset, midnight, all compressed into a span shorter than a work shift. The moon changed that. Its gravitational pull created enormous tides in the young Earth's oceans, and these tides acted as a brake, a friction converting rotational energy into heat and gradually slowing Earth's spin. The closer the moon was, the stronger this effect, so the early slowdown was dramatic. As Earth slowed, the moon retreated, moving into higher orbits. The two processes are linked. Earth's lost rotational energy becomes the moon's orbital energy. It's a slow transfer, a cosmic exchange that's been happening for billions of years and continues today, though at a much reduced rate now that the moon is farther away. Without the moon, Earth might still be spinning rapidly, days too short for complex life to establish stable circadian rhythms. The moon gave us time, in a very literal sense, stretching our days from frantic hours into the comfortable 24-hour cycle we know, time enough for sleep, for growth, for the rhythms of life to synchronize with light and darkness. The moon has no seas of water, but the names persist from when 17th century astronomers hoped they were real. Mare Imbrium, Mare Serenitatis, Oceanus Procellarum, the Sea of Rains, the Sea of Serenity, the Ocean of Storms. These names carry a longing, don't they? A hope that the moon might be like Earth, with waters and shores, places where ships might sail under alien stars. When 17th century astronomers first turned telescopes toward the moon, they saw dark, smooth regions that looked like they could be bodies of water. They named them Maria, seas, and imagined a moon with oceans, perhaps even life. It was a natural assumption. a projection of Earth onto the unknown. But there are no seas on the moon. There never were. The dark regions are lava flows. Stone so ancient it makes Earth's oldest rock seem young. The names remain, though, poetic and beautiful, maps drawn from wishes rather than reality. We still say we're looking at the Sea of Tranquility, even knowing it's nothing but cold, dark basalt, dry and dead for over 3 billion years. Perhaps there's something fitting about keeping these names. They remind us that science begins with wonder, with hope, with the very human tendency to see ourselves reflected in the cosmos. We were wrong about the seas, but we were right to look, right to wonder, right to give names to the mysterious places we saw. The moon's gravitational pull is stronger on the side of Earth facing it than the far side. Gravity weakens with distance. This is fundamental physics, inescapable. The moon pulls on Earth, but it pulls harder on the parts of Earth that are closer to it, the near side, and more weakly on the parts that are farther away, the far side. This difference, this gradient in gravitational pull, is what creates tides. Water on the near side is pulled more strongly toward the moon and bulges outward. Water on the far side is pulled less strongly than Earth as a whole, so it bulges outward in the other direction, left behind by the rest of the planet. The result is two tidal bulges on opposite sides of Earth. As Earth rotates beneath these bulges, any given point on the surface passes through both of them, experiencing 2 high tides and 2 low tides each day. It's not the moon pulling water toward it. Exactly. It's the difference in the moon's pull across Earth's diameter, stretching our planet slightly into an oval shape, creating the tides we see. This same gradient creates stress in Earth's crust, generating those 12-inch crustal tides. It heats the moon's interior slightly through tidal flexing. It's even slowing Earth's rotation. All from a simple fact: gravity is weaker at greater distances, and the difference stretched across planetary scales becomes powerful enough to move oceans. The moon is the 5th largest moon in our solar system, larger than Pluto. When we think of moons, we often think of small objects, minor companions to massive planets. But the moon is substantial. It's the 5th largest natural satellite in the solar system, after Ganymede, Titan, Callisto, and Io, all of which orbit gas giants much larger than Earth. The moon has a diameter of about 2,159 miles. That's larger than Pluto, which is only about 1,476 miles across. It's about 1/4 the diameter of Earth, which is an unusually large ratio for a moon-to-planet system. Most moons are tiny compared to their parent planets, but the moon is significant, substantial, almost a world in its own right. This has led some astronomers to suggest that Earth and Moon should be classified as a double-planet system, rather than a planet and its satellite. The Moon is large enough, and its gravitational influence on Earth significant enough, that the two bodies orbit around a common centre of mass, the barycenter, which lies about 1,000 miles beneath Earth's surface. We're not just a planet with a moon, we're two worlds locked in a mutual dance, each affecting the other in profound ways. The moon's surface contains the same elements as Earth's mantle, supporting the giant impact theory. When scientists analysed the lunar samples brought back by Apollo, they found something telling. The chemical composition of lunar rocks closely matches Earth's mantle. Not Earth as a whole, but specifically the mantle, the layer beneath the crust, above the core. This is strong evidence for the giant impact theory. If the moon formed from debris blasted off Earth's outer layers during the Theia collision, you'd expect it to be made primarily of crustal and mantle material, with very little iron from Earth's core. And that's exactly what we see. The isotopic ratios are particularly striking. Oxygen isotopes in lunar rocks are virtually identical to those in Earth's mantle, a kind of chemical fingerprint showing a shared origin. If the moon had formed independently or been captured from elsewhere in the solar system, it would have different isotopic ratios, a different chemical signature. The moon is literally made of Earth, scattered and reformed. When you look up at the moon, you're seeing part of our own planet, torn away by ancient violence and reshaped into a new world. We're connected not just by gravity but by substance, by material, by atoms that once belonged to a single body before catastrophe split them apart. The moon has been worshipped as a deity in nearly every ancient culture throughout human history. The moon has always been more than just a celestial object to humanity. It's been a god, a goddess, a symbol, a calendar, a guide. Every ancient culture we know of incorporated the moon into their religious and mythological frameworks. In Greek mythology, Selene drove a silver chariot across the night sky. In Roman tradition, Luna watched over childbirth and the cycles of women. In Mesopotamian belief, Sin or Nana was a powerful deity whose phases governed time itself. In Hindu tradition, Chandra rides across the heavens, waxing and waning in eternal cycles. Indigenous cultures worldwide saw the moon as a powerful spirit, sometimes male, sometimes female, always significant. This universality makes sense. The moon is visible, predictable, changeable, yet regular. Its phases provided an easy calendar for tracking time before written records. Its light allowed navigation at night. Its cycles seemed to mirror biological rhythms, menstruation, tides, perhaps even moods and behaviors. Even now, in an age of science, the moon retains a kind of sacred quality in human consciousness. We still find it romantic, mysterious, worthy of poetry and art. We've walked on it, analysed its rocks, mapped its surface, but we haven't entirely demystified it. It remains what it's always been, a presence in our sky, ancient and patient, watching our species evolve from cave dwellers to spacefarers. The moon's orbit is tilted about 5 degrees relative to Earth's orbit around the sun. The moon doesn't orbit Earth in the same plane that Earth orbits the sun. Its orbital plane is tilted by about 5 degrees, which might not sound like much, but it's crucial for understanding eclipses. If the moon orbited in the same plane as Earth's orbit around the sun, we'd have eclipses every month, a solar eclipse at every new moon, a lunar eclipse at every full moon. But because of this 5-degree tilt, most months the moon passes above or below Earth's shadow during full moon, and above or below the line connecting Earth and Sun during new moon. Eclipses only happen when the moon crosses the ecliptic plane at the same time it's in the new or full phase. This crossing happens at points called nodes, and the nodes themselves slowly rotate over time, completing a full cycle every 18.6 years. This creates patterns in eclipse timing, the Saros cycle, used by ancient astronomers to predict eclipses. They didn't understand orbital mechanics, but they recognized the pattern. Eclipses repeat in series, separated by about 18 years, because the geometry eventually repeats itself. That 5-degree tilt makes eclipses special, rare enough to be noteworthy. If the orbits were aligned, eclipses would be mundane, monthly occurrences. The tilt gives them significance, makes them worth travelling to witness, worth remembering. And the Moon has boulder fields where massive rocks have rolled down crater walls, leaving tracks behind them. On some crater walls, enormous boulders, some as large as houses, have broken loose and rolled downhill, bouncing and tumbling under the Moon's weak gravity. And because there's no wind or rain to erase them, the tracks these boulders leave remain perfectly preserved, dark trails showing their entire journey from rim to floor. High-resolution images from lunar orbit show these tracks clearly, meandering lines showing where boulders rolled, bounced, changed direction after hitting obstacles, finally coming to rest at the bottom. Some tracks are miles long, recording journeys that took place thousands or millions of years ago but look like they happened yesterday. What caused the boulders to fall? And some were dislodged by meteor impacts shaking the crater walls. Others may have been freed by thermal stress. The extreme temperature changes between lunar day and night causing rocks to expand and contract, eventually cracking and breaking free. A few might have been dislodged by moonquakes. Whatever the cause, once they started rolling, they followed the gentle pull of lunar gravity, tumbling in slow motion down slopes, leaving permanent records of their paths. The Moon preserves motion, freezes it into the landscape, creating a kind of geological animation that can be read like a story. The Moon experiences transient lunar phenomena, brief flashes and glows reported by observers for centuries. For hundreds of years, observers have reported strange, brief phenomena on the Moon, flashes of light, glows, obscurations, as temporary changes in appearance. These are called transient lunar phenomena, or TLPs, and they remain somewhat mysterious. Most TLPs are probably explained by known processes. A bright flash might be a meteor impact, vaporizing on contact and creating a brief glow. A reddish discoloration might be outgassing from beneath the surface, releasing trapped volatiles that scatter light. Some reports are likely optical effects, light interacting with Earth's atmosphere in unusual ways, creating apparent changes on the Moon that aren't really there. But a few observations remain unexplained. Repeated sightings in specific locations like the crater Aristarchus suggest something might genuinely be happening there. Perhaps outgassing, perhaps something else. Without continuous monitoring and better instruments, it's hard to say for certain. The Moon is not entirely inert. It still has processes, still changes in small ways. These transient phenomena remind us that even a dead world can surprise us, that there are still mysteries waiting on that ancient familiar surface. The Moon's regolith can be sintered into construction materials using only focused sunlight. Future lunar colonists won't need to bring building materials from Earth. The lunar soil itself, that fine grey regolith covering the surface, can be transformed into construction material using nothing but sunlight and simple equipment. The process is called sintering, heating powder until the particles fuse together without fully melting. On the Moon, you could use mirrors or lenses to focus sunlight onto regolith, heating it to temperatures high enough that the particles stick together, forming solid blocks or bricks. No cement needed, no water, no complex chemistry, just dirt and sunlight. This is enormously valuable for future lunar bases. Launch costs from Earth are measured in thousands of dollars per pound, making it prohibitively expensive to ship construction materials. But if you can make bricks from local soil, you can build habitats, landing pads, roads, walls, entire structures assembled from the ground beneath your feet. Some researchers have even suggested using large solar concentrators or even lasers to sinter regolith in place, creating roads or landing pads without having to shape individual bricks. You'd literally pave the moon using sunshine, turning dust into stone, building infrastructure from the landscape itself. The moon providing its own materials, humanity providing the tools and knowledge to shape them. The moon has no intrinsic light. Everything we see is reflected sunlight, making it essentially a giant mirror. The moon doesn't glow, it has no light of its own, no internal luminescence, no radiance except what it borrows from the sun. Every photon that reaches your eye from the moon started at the sun, travelled 93 million miles to the lunar surface, bounced off rock and dust, and travelled another 250,000 miles to Earth. We call it moonlight, and it feels different from sunlight, cooler, gentler, mysterious. But it's the same light, just reflected, filtered by the moon's dark basalt and bright highlands. The moon is, in essence, a mirror, though not a particularly good one. It only reflects about 12% of the light that hits it, absorbing the rest. That 12% is enough to cast shadows on Earth during a full moon, enough to light your way on a dark night, enough to inspire countless poems and songs. But its borrowed glory, reflected radiance. The moon is a dark object made bright by proximity to the sun, a reminder that brightness isn't always intrinsic, that sometimes what we shine with comes from somewhere else. The moon's formation may have briefly turned Earth into a molten hellscape covered in a magma ocean. The collision that created the moon released energy almost beyond comprehension. When Theia struck Earth, the impact vaporized rock, created temperatures hot enough to turn stone into gas, and likely melted most or all of Earth's surface, creating what scientists call a magma ocean. Picture Earth in those first hours and days after impact. A glowing sphere of molten rock, its surface a sea of lava thousands of miles deep, still churning from the violence that created it. The sky filled with vaporized stone, the remnants of two worlds mixing and beginning to separate. Some material falling back to Earth, some coalescing into what would become the moon. This magma ocean took millions of years to cool and solidify. As it cooled, different minerals crystallized at different temperatures, separating by density. Lighter minerals floated to form the crust. Heavier minerals sank toward the mantle. The entire planet reorganized itself, stratifying into layers as it cooled from the worst day in its history. And through it all, the moon was there, newly formed, glowing with its own heat, orbiting a planet that was still cooling from the impact that birthed them both. Two worlds, born from catastrophe, and gradually settling into the forms we recognize today. The moon's synchronous rotation developed over time due to tidal friction with Earth. The moon didn't always show us the same face. Billions of years ago, when it first formed, the moon rotated faster, spinning on its axis in a matter of hours or days, showing all its faces to Earth as it orbited. But Earth's gravity pulled on the moon unevenly. The near side experienced stronger gravitational pull than the far side, creating a tidal bulge in the moon itself, the solid rock stretching slightly toward Earth. As the moon rotated, this bulge tried to rotate with it, but Earth's gravity pulled it back, creating friction, generating heat, slowing the moon's rotation. Over millions of years, this tidal friction gradually slowed the moon's spin until it matched its orbital period exactly. The bulge locked into place, always facing Earth, and the moon's rotation stabilized into the synchronous state we see today. one rotation per orbit, the same face eternally watching Earth. This is a common fate for moons close to their parent planets. Most large moons in the solar system are tidally locked to their planets. It's a kind of gravitational inevitability, time and friction eventually winning out over rotation, settling into the most stable configuration. The moon's current state isn't special or designed. It's just what happens when you orbit a planet for long enough. The moon has ghost craters, ancient impacts almost completely buried by later lava flows. In the Maria, if you look carefully at high-resolution images, you can sometimes see faint circular outlines, rings barely visible in the dark basalt, subtle variations in colour or texture that trace the edges of ancient craters. These are ghost craters, impacts that formed before the lava flows, then were nearly erased when molten rock flooded the basins. The lava didn't quite fill these craters completely. It covered them, yes, but left subtle traces, a slight depression where the crater floor lies beneath the lava, a faint difference in how the surface weathered over billions of years. Sometimes just the rim pokes through the lava, a broken circle of highlands surrounded by dark mare. These ghost craters are time markers. They're older than the Maria, predating the lava flows by millions or hundreds of millions of years. They show that the moon's surface has layers of history, events piled on events, some buried, some visible. Yes, some preserved only as faint traces detectable only from orbit. Walking across a mare, you'd never know these ghost craters were there beneath your feet. But from above, with the right lighting and instruments, they reveal themselves. Phantoms of impacts long past, buried but not quite forgotten, waiting patiently to be noticed. The moon's soil contains helium-3, a rare isotope that could potentially fuel future fusion reactors. Buried in the lunar regolith is a substance that's extraordinarily rare on Earth but relatively common on the moon. Helium-3, a light isotope of helium with one less neutron than the common helium-4. It's been delivered to the moon by solar wind over billions of years, implanted into the surface grain by grain. On Earth, helium-3 is so rare it's measured in kilograms worldwide. But on the moon, estimates suggest there could be millions of tons of it mixed into the regolith, concentrated near the surface where solar wind has the most access. Why does this matter? Helium-3 is a potential fuel for nuclear fusion reactors, cleaner and safer than deuterium-tritium fusion, producing less radioactive waste and more energy. If fusion power ever becomes practical, helium-3 could be an ideal fuel, and the moon could be the source. This has led some to speculate about future helium-3 mining operations on the moon. Massive strip mining of regolith, heating it to release trapped gases, collecting the helium-3 and shipping it back to Earth, or using it in lunar fusion plants. The moon as an energy source, its soil literally containing fuel harvested from the sun over eons, waiting to be extracted and used. The moon is gradually moving into a higher orbit, though this process is incredibly slow. The moon is leaving us, not quickly, not dramatically, but steadily, reliably, about 1.5 inches farther away each year. It's been doing this since it formed, gradually spiraling outward, climbing to higher orbits. This happens because of the same tidal friction that slowed the moon's rotation and is slowing Earth's rotation. Energy is transferred from Earth's rotation to the moon's orbit. Earth spins slower, the moon climbs higher. It's a conservation of angular momentum. The total spin of the Earth-Moon system must be conserved, so as one decreases, the other increases. In about 50 billion years, if nothing else intervened, Earth and Moon would reach a stable equilibrium, when Earth's rotation would slow to match the Moon's orbital period, about 47 current days, and both would be tidally locked to each other, always showing the same faces, circling at a much greater distance than they do now. But the Sun won't allow this to happen. In about 5 billion years, the Sun will expand into a red giant, swelling until it consumes Mercury, Venus, possibly Earth, almost certainly the Moon. The slow dance between Earth and Moon will end not in equilibrium but in fire. Both worlds vaporize before they can reach that final stable configuration. The Moon's coldest permanently shadowed craters are colder than the surface of Pluto. Pluto is famous for being cold. Temperatures there hover around negative 375 degrees Fahrenheit on average. But some places on the Moon are colder. The permanently shadowed craters near the lunar poles reach temperatures as low as negative 400 degrees Fahrenheit, colder than anywhere else in the inner solar system. This happens because these craters never receive direct sunlight. They're trapped in eternal shadow, never warming, only radiating heat away into space. Over billions of years, they've cooled to temperatures approaching the cosmic background radiation, the faint warmth left over from the Big Bang itself. These extreme temperatures create natural cryogenic freezers, preserving volatile materials that would evaporate anywhere else on the Moon. Water ice, yes, but potentially other compounds too. Ammonia, methane, carbon dioxide, organic molecules. These craters are laboratories of sorts, preserving samples of material delivered to the Moon over its entire history. Frozen in place, waiting to be studied. Scientists have even speculated that complex organic molecules, perhaps the building blocks of life, might be preserved in these cold traps, delivered by comets billions of years ago, and kept frozen ever since. The Moon's coldest places might hold clues not just to lunar history, but to the chemistry that led to life itself. The Moon has rills, channel-like depressions carved by ancient flowing lava. Snaking across the lunar surface, especially in and near the Maria, are long, winding channels called rills. They look like dried riverbeds, sometimes hundreds of miles long and several miles wide, meandering across the landscape in curves that seem almost fluid. But no water carved these channels. They were created by lava, either flowing across the surface in channels that later cooled and subsided, or flowing underground in lava tubes whose roofs later collapsed, exposing the channels beneath. Some rills are remarkably straight, carved quickly by high-volume flows. Others meander like rivers, suggesting slower flows that changed course over time as topography directed them. A few have features that look like terraces, showing different levels where lava flowed at different heights before draining away. One of the most famous is Hadley Rill, explored by Apollo 15 astronauts David Scott and James Irwin. They drove their lunar rover along its edge, photographing the steep walls and collecting samples of exposed bedrock. Standing at the edge, looking down into a channel carved by lava billions of years ago, they were witnessing geology on a scale impossible to experience on Earth, but where erosion would have long since erased such features. The Moon's gravitational pull varies slightly across its surface due to mass concentrations underground. If you could measure gravity precisely while walking across the Moon's surface, you'd find subtle variations, places where you weigh slightly more or less depending on what's beneath your feet. These variations are caused by maskons, those hidden concentrations of dense material beneath the Maria. The differences are small, a fraction of a percent, but they're real and measurable. Over a large mascon, gravity might be a few tenths of a percent stronger than average. Walk away from the mascon toward the highlands, and gravity weakens slightly. These variations affect spacecraft in orbit more dramatically than surface explorers. A satellite passing over a mascon experiences increased gravitational pull, which speeds it up and pulls it into a lower orbit. Without constant adjustments, lunar satellites would eventually crash due to these gravitational anomalies. Mapping these gravity variations has been crucial for understanding the Moon's internal structure. By measuring how gravity changes across the surface, scientists can infer what's underground, where the crust is thick or thin, where dense materials lie, how the basins are structured beneath the lava flows. Gravity becomes a tool for seeing through rock, revealing hidden architecture. The Moon's ancient volcanic activity ceased about 1 billion years ago, leaving a cold, dead world. There was a time when the Moon was geologically alive. Volcanoes erupted, lava flowed across vast plains. The interior churned with heat. But that time is long past. The last volcanic eruptions on the Moon happened roughly 1 billion years ago, give or take a few 100 million years, and since then, nothing. Silence. Stillness. 1 billion years is almost incomprehensible. When the Moon's last volcano went quiet, Earth was in the Proterozoic era. Life existed, but only as single-celled organisms and simple multicellular forms. There were no plants, no animals, no eyes to see, no brains to wonder about the Moon above. The Moon went geologically dead before complex life even began. Since then, the Moon's interior has cooled and solidified. Whatever heat remained from its formation, whatever radioactive decay still warmed its core, it wasn't enough to drive volcanic activity. The Maria we see today are frozen snapshots of the Moon's active period, the last flows preserved exactly as they solidified, never buried by new eruptions, never recycled by plate tectonics. The Moon is a world where geology has ended. All that remains is the slow work of impacts and space weathering, processes that don't create new landforms but merely modify old ones. It's a kind of death, though perhaps death is the wrong word. The Moon has simply finished, settled into its final form, and now it waits, unchanging, for whatever comes next. The Moon experiences meteor showers just like Earth, though without an atmosphere to create streaks of light. Earth passes through streams of debris left by comets, and when it does, we see meteor showers, the Perseids, the Leonids, dozens of meteors per hour streaking across the sky, burning up as they hit our atmosphere. The Moon experiences the same thing. When Earth passes through a debris stream, so does the Moon, being bombarded by the same particles. But on the Moon, there's no atmosphere to create those beautiful streaks of light. Instead, each meteor strikes the surface directly, vaporizing on impact in a brief flash visible only with sensitive instruments. No trails, no glowing arcs across the sky, just tiny explosions, silent and sudden. During a major meteor shower, the Moon's surface experiences hundreds or thousands of impacts per hour. Most are tiny microscopic dust grains that barely disturb the regolith, but occasionally something larger hits, pebble-sized or larger, creating a flash bright enough to be seen from Earth with telescopes. Astronomers have recorded these impact flashes during meteor showers, watching the Moon's dark side light up with brief sparkles as debris strikes. It's a strange inversion of what we experience on Earth. We see meteors burning harmlessly high in our atmosphere. The Moon sees nothing, feels nothing, but takes the full force of the impacts, adding new craters to its already scarred surface. The Moon's interior may still contain a partially molten layer deep beneath the surface. Despite being geologically dead at the surface, the Moon's deep interior may not be entirely solid. Seismic data from the Apollo missions suggests there might be a partially molten layer surrounding the core, a zone where rock is soft, warm, perhaps liquid in places. This layer would be small, representing only a tiny fraction of the Moon's volume, and it's not actively driving geological processes like it would on Earth, but its existence would tell us something important about the Moon's thermal history, about how much heat it retained from formation, and how slowly it's been cooling. The evidence isn't conclusive. The Apollo seismometers operated for only about 8 years, and they were all on the near side, giving limited coverage. Interpreting seismic waves travelling through the Moon's interior is difficult with such limited data. Scientists can infer structure, but there's uncertainty, room for different interpretations. Future missions might settle the question. New seismometers, placed at different locations including the far side, operating for years or decades, could map the Moon's interior with much greater precision. Until then, the Moon keeps its deepest secrets hidden. The warmth at its core, if warmth remains, unconfirmed but possible, a last remnant of fire in an otherwise frozen world. The Moon has no river valleys, but it does have rills that resemble dried-up riverbeds. At first glance, lunar rills look remarkably like river valleys on Earth, winding channels with tributaries, meandering paths that follow topography, features that seem carved by flowing liquid. But no water created them. They're lava channels carved by molten rock flowing across the surface billions of years ago. The resemblance is striking enough that early observers, looking through telescopes, sometimes mistook them for evidence of water on the Moon. Even knowing their volcanic features, it's hard not to see them as rivers when you look at photographs. The mind insists on the comparison, and this similarity comes from the physics of flowing liquids. Whether water or lava, liquids flow downhill, follow the path of least resistance, meander when the gradient is shallow, carve channels through softer materials. The specific details differ. Lava is more viscous, hotter, chemically different. But the basic behaviour is similar enough to create landforms that look related. It's a kind of convergent evolution in geology. Different processes creating similar forms because they're governed by the same fundamental laws of physics. The Moon has no rivers, never had rivers, but it has features that speak the same visual language, channels carved by flow, preserved perfectly in the absence of the very thing, water, that might have erased them. The Moon's surface is constantly bombarded by solar wind particles, gradually changing its chemistry. The Sun doesn't just give us light and heat, it also emits a constant stream of charged particles, electrons and protons primarily, travelling outward at hundreds of miles per second. This is the solar wind, and it blasts the Moon's unprotected surface continuously, day and night, for billions of years. On Earth, our magnetic field deflects most of these particles, protecting the surface. But the Moon has no such protection. Solar wind strikes the surface directly, embedding itself in rocks and soil, creating chemical reactions, breaking molecular bonds, darkening materials. This process, called space weathering, gradually changes the Moon's appearance. Fresh, newly exposed material is bright and reflective. Over millions of years, solar wind bombardment darkens it, creating the subtle colour variations we see in high-resolution images. The bright rays around young craters are fresh material that hasn't been darkened yet. Give them time, hundreds of millions of years, and they'll fade, blending into the background. Space weathering also creates interesting chemistry. Solar wind carries hydrogen, which combines with oxygen in lunar minerals to create trace amounts of water and hydroxyl compounds. The moon is constantly making tiny amounts of water at its surface through this process, though most of it is immediately lost to space. A few molecules might migrate to cold traps and freeze, but most escape, only to be replaced by new molecules created by the next batch of solar wind. The moon has peaks that rise over 16,000 feet, though they look gentle due to the lack of erosion. The moon has mountains, substantial ones, some over 3 miles high. The Leibniz and Duerfell mountains near the South Pole reach altitudes over 16,000 feet, comparable to mountains in the Alps or Rockies. The Montes Apenninus, forming part of the rim of Mare Imbrium, has peaks exceeding 15,000 feet. But lunar mountains look different from Earth's mountains. They're rounded, gentle, worn-looking, not from erosion, but because they formed differently. Most lunar mountains are the rims of ancient impact basins, massive crater walls created by impacts so large they reshaped the moon's crust. These walls slumped and settled over time under the moon's gravity, creating the smooth, rolling profiles we see today. Without wind or water to sharpen them, without plate tectonics to thrust them upward and create jagged peaks, lunar mountains maintain the forms they had when they first settled billions of years ago. They're mountains frozen in time, neither growing nor shrinking, just sitting there in patient stillness. Climbing a lunar mountain would be strange. The weak gravity would make ascent easier. You could carry more gear, take longer strides, jump higher. But there would be no streams to cross, no vegetation to push through, no soil, just bare rock and dust, the same grey-brown everywhere, slopes that go on and on without the visual landmarks that erosion creates. The moon's gravity is strong enough that dust can't escape, but weak enough that jumping is easy. The moon's gravity exists in an interesting middle ground. It's strong enough to hold onto the regolith, to keep rocks from drifting away, to create a meaningful sense of down. Nothing on the surface naturally escapes into space, but it's weak enough that human movement becomes almost effortless. The Apollo astronauts discovered this immediately. Despite wearing spacesuits that weighed over 180 pounds on Earth, they could hop, skip, even bounce on the surface with ease. John Young, during Apollo 16, jumped straight up and managed to get about a foot off the ground while saluting the flag. Something impossible on Earth in that suit. The astronauts developed a peculiar hopping gait for moving around, more efficient than walking in the low gravity. This creates interesting possibilities for future lunar activities. Sports would be transformed. Imagine basketball where you could jump 10 feet high, or long jump competitions where 60-foot leaps are possible. Construction would be easier, with workers able to move heavy objects and climb structures with minimal effort. Even daily life would have different rhythm, movement requiring less energy, heights less threatening. But the weak gravity also creates challenges. Objects don't fall predictably when you're used to Earth's pull. Dropped tools fall slowly, giving you time to catch them, but also time to forget about them. Thrown objects travel in long, flat arcs. You'd have to relearn basic physics, recalibrate your intuition for how things move and fall. The moon has ancient magnetic stripes similar to those found on Earth's ocean floors. When scientists mapped the moon's magnetic field from orbit, they found something unexpected. long linear magnetic anomalies arranged in parallel stripes across certain regions, particularly in areas opposite major impact basins. This pattern resembles the magnetic stripes found on Earth's ocean floors, are created when molten rock solidifies in the presence of Earth's magnetic field, preserving a record of the field's orientation. When Earth's magnetic field reverses polarity, which it does every few 100,000 years, new rock records the new orientation, creating alternating stripes of opposite magnetic polarity. Could the same process have happened on the Moon? Possibly. If the Moon had a magnetic field that reversed polarity while lava was flowing across the surface, it might have created similar stripes. But the pattern isn't quite as clear as on Earth, and there are other possible explanations. One intriguing theory suggests these magnetic stripes formed from debris impacts on the opposite side of the Moon. When a massive asteroid struck, it vaporized rock and created a plasma cloud that expanded outward. This plasma might have carried and amplified magnetic fields, which then imprinted on the surface at the antipodal point, the spot directly opposite the impact. It's a strange mechanism unique to airless bodies, creating magnetic patterns through catastrophe. The Moon's surface contains enough titanium to be potentially worth mining in the future. Hidden in the dark basalts of the Luna Maria are valuable minerals, particularly ilmenite, an iron titanium oxide. Some Maria have titanium concentrations several times higher than typical Earth deposits, locked in minerals that formed when ancient lava flows crystallized. Titanium is valuable on Earth. Strong, light, corrosion-resistant, used in everything from aircraft to medical implants. It's also difficult and energy-intensive to extract from ore. On the Moon, as you'd face the same challenges, plus the difficulty of operating in vacuum and dealing with lunar dust. But if humans establish a permanent presence on the Moon, local resources become increasingly attractive. Mining lunar titanium might make sense not for shipping back to Earth. Launch costs would be prohibitive, but for use in lunar manufacturing. Build structures, tools, equipment from materials you find rather than shipping everything from Earth. The same applies to other minerals: aluminum, silicon, iron, oxygen, all abundant on the Moon, all potentially extractable with the right equipment and energy. The Moon could become self-sufficient, a place where industry uses local resources to build and expand, where the only imports from Earth are things that can't be made locally: electronics, complex machinery, perhaps people. It's a vision of the future where the Moon transitions from destination to colony, from place we visit to place we live, extracting value from the ancient rocks beneath our feet. The Moon's orbit is slowly expanding, but it will never escape Earth's gravitational embrace. Despite drifting steadily outward, despite gaining orbital energy from Earth's rotational energy, the Moon will never escape. It will never wander off into space to become an independent planet. Earth's gravity, even weakened by distance, will hold it indefinitely. The physics is straightforward. To escape Earth's gravitational influence entirely, the Moon would need to reach escape velocity, about 25,000 miles per hour relative to Earth. But the tidal forces that are pushing the Moon into higher orbits are also slowing Earth's rotation, and there's only so much rotational energy available to transfer. Long before the Moon could gain enough energy to escape, Earth's rotation will have slowed to the point where both bodies are tidally locked to each other, both showing the same faces forever, orbiting at a distance much greater than now, but still firmly bound together. And even that won't happen, because the Sun will intervene. In about 5 billion years, the Sun will expand into a red giant phase, swelling enormously, potentially engulfing Earth, and almost certainly the Moon. The slow dance between Earth and its companion will end not in separation, but in destruction, both consumed by the dying star that gave them light for so long. So the Moon remains our permanent companion, bound to us by gravity, by history, by the circumstances of its violent birth. It's not going anywhere, not really, except farther away in a retreat that will never quite become departure. The Moon has no ionosphere to reflect radio waves, making long-distance communication difficult without satellites. On Earth, we can communicate over great distances using radio waves that bounce off the ionosphere, a layer of charged particles in the upper atmosphere. This reflection allows radio signals to travel beyond the horizon, around the curve of the planet. It's how early long-distance radio communication worked before satellites. The Moon has no ionosphere. There's no atmosphere to ionize, no layer to reflect radio signals. Radio waves travel in straight lines, and anything beyond the horizon is completely unreachable. This created a problem for the Apollo missions. When the command module orbited behind the Moon, like carrying an astronaut while his two crewmates explored the surface, he lost all contact with Earth. The Moon itself blocked the signal. For about 45 minutes each orbit he was alone, more alone than any human had ever been, cut off from every other person in existence, separated by 250,000 miles in a world of solid rock. The astronauts on the surface faced similar limitations. They couldn't communicate directly with Earth when on the far side, and their range on the near side was limited by the horizon. Everything had to relay through the command module overhead, and even that was only possible when it was in view. Future lunar bases will need satellite networks, relay stations positioned around the Moon to maintain constant communication. Without them, exploration of the far side remains isolated, cut off. A return to the age before radio, when distance truly meant silence. The Moon's surface is covered in microscopic glass spherules created by meteor impacts melting and flash-cooling regolith. If you could examine lunar soil under a microscope, you'd find it full of tiny glass beads. Spherules, scientists call them. Perfect little spheres ranging from microscopic to the size of sand grains. They're beautiful, actually, catching light in surprising ways, each one a frozen droplet of molten rock. These form during meteor impacts. When a meteorite strikes at high velocity, it generates tremendous heat, enough to melt rock and soil. Some of this molten material is thrown into the airless sky as droplets, without air resistance. These droplets maintain spherical shapes, surface tension pulling them into perfect spheres, and they cool rapidly in the vacuum, solidifying into glass before they land. The result is soil that sparkles. When sunlight hits lunar regolith at the right angle, these tiny glass beads catch and reflect the light, giving the surface a subtle shimmer. Astronauts notice this, reporting that the soil sometimes seemed to glow or glitter, particularly around sunrise when low-angle light enhanced the effect. Each spherule is a miniature record of an impact, a moment of violence frozen into beauty. The Moon has been creating these for billions of years, each meteor strike adding more glass to the soil, until now the regolith is thoroughly mixed with them. Billions upon billions of tiny glass beads covering the surface, waiting to catch the light. The Moon has experienced at least 5,000 moonquakes detected by seismometers left by Apollo missions. Between 1969 and 1977, The seismometers left by Apollo missions recorded thousands of moonquakes, at least 5,000 detected events, probably many more too small to register clearly. These quakes revealed a moon that, while geologically quiet compared to Earth, still has internal processes, still moves and shifts in subtle ways. The most mysterious are the deep moonquakes, originating hundreds of miles below the surface. These occur with strange regularity, clustering around the times when the moon is closest to Earth in its elliptical orbit. The extratidal stress from Earth's gravity, pulling and squeezing the moon more strongly at perigee, apparently triggers these deep tremors. There are also shallow moonquakes, are much stronger and more concerning for future lunar bases. Some of these reach magnitude 5.5 on the Richter scale, strong enough to damage structures on Earth. And they last much longer than earthquakes, reverberating through the moon's interior for 10 minutes or more, that strange ringing quality physicists noticed. Then there are thermal moonquakes, caused by the surface expanding and contracting as it heats and cools during the long lunar day and night. And impact moonquakes, triggered by meteorites striking the surface, sending vibrations through the entire body of the moon. All of this was unexpected. Before Apollo, many scientists thought the moon was completely inert, a dead ball of rock with no internal activity. These seismometers proved otherwise, revealing a world still adjusting to ancient stresses, still moving in slow, patient ways. The moon's apparent size in the sky matches the sun's so precisely that this may have helped ancient astronomers. The fact that the moon and sun appear almost exactly the same size in our sky isn't just a cosmic coincidence that makes eclipses possible. It may have been scientifically useful to ancient astronomers trying to understand the heavens. During total solar eclipses, when the moon precisely covers the sun's bright disk, the sun's corona becomes visible, that faint ethereal atmosphere extending millions of miles into space, normally invisible against the sun's blazing surface. Ancient observers during eclipses could see this corona, could watch solar prominences arc up from the edge, could study the sun in ways impossible any other time. These observations, recorded by cultures around the world, helped early astronomers understand that the sun had structure, had an atmosphere, was more than just a disk of light. The moon, by perfectly covering the sun's face, acted like a scientific instrument, a natural coronagraph allowing observations that wouldn't be possible again until we developed sophisticated telescopes and filters. This perfect sizing also helped ancient astronomers calculate distances and sizes. If the moon exactly covers the sun, they must subtend the same angle in the sky, which means their actual sizes must be proportional to their distances. Aristarchus of Samos used eclipse observations to estimate the relative sizes and distances of the sun and moon, arriving at values impressively close to reality given his limited tools. The moon taught us about the sun, about geometry, about our place in space, all because of this one remarkable coincidence of size and distance. The moon has ancient swirl patterns on its surface that don't correlate with any geological features. Among the moon's many mysteries, the swirls might be the most visually striking. These are bright, sinuous patterns that wind across the surface, completely unrelated to topography. They're not ridges or valleys. You could walk across one and never know it was there. They're purely albedo features, differences in brightness visible only from above. The most famous is Rhina Gamma, a bright swirl in Oceanus Procellarum that looks almost painted on, a looping pattern that seems decorative, intentional. But it's not artificial, and we're still not entirely sure how it formed. The leading theory connects them to magnetic anomalies. Where crustal rocks retain ancient magnetism, the weak magnetic fields deflect solar wind particles, protecting the surface from space weathering. Protected areas stay brighter while surrounding regions darken over millions of years, creating these ghostly patterns. But questions remain. How did the magnetic anomalies form in these specific patterns? Why are they often at antipodal points from major impact basins? Do they represent something about the Moon's ancient magnetic field, or are they created by impacts in ways we don't fully understand? The swirls are beautiful regardless of their origin. Bright cursive script written across the Moon's face in a language we're still learning to read. Patterns that suggest meaning we haven't quite grasped. The Moon's limb, edge, reveals subtle changes during each orbit due to libration effects. Now watch the Moon carefully over the course of a month, and you'll notice something subtle. Features near the edge appear and disappear, sliding in and out of view. The Moon seems to rock gently back and forth, nod up and down, revealing glimpses of what lies just beyond the edge. This is libration, not actual rotation, but apparent wobbling caused by the Moon's elliptical orbit, its tilted axis, and the fact that it rotates at constant speed while its orbital velocity varies. When the Moon is at perigee, moving faster in its orbit, its rotation can't quite keep up, and we see a bit around the western edge. At apogee, moving slower, we see around the eastern edge. Similarly, the Moon's axis is tilted slightly relative to its orbital plane, so sometimes we see a bit over the North Pole, sometimes over the South. These librations combine to let us see over time about 59% of the Moon's surface from Earth, instead of just 50%. For patient observers, libration creates opportunities. Features normally right at the edge become more visible, easier to photograph and study. Craters that are usually foreshortened can be seen more directly. The Moon reveals its secrets slowly, a little at a time, rewarding those who watch carefully and wait. The Moon may have briefly had a thicker atmosphere billions of years ago during intense volcanic activity. Imagine the Moon surrounded by a thin but real atmosphere, thick enough to scatter light, to create weather of sorts, to carry sound. This might have actually happened, briefly, during the era of intense volcanic activity billions of years ago. When volcanoes erupt, they release gases, water vapor, carbon dioxide, sulfur compounds. On Earth, these gases join the existing atmosphere. But the Moon had no atmosphere to begin with, so volcanic gases would have accumulated, potentially creating a temporary thin atmosphere during periods of intense eruption. Scientists estimate that during peak volcanic activity, the Moon might have had an atmosphere about half as thick as Mars's current atmosphere. Not breathable, not protective, but substantial enough to alter the Moon's appearance from Earth, to create subtle effects, maybe even brief periods of transport and deposition, different from the vacuum conditions we see now. This atmosphere wouldn't have lasted. The Moon's weak gravity couldn't hold on to gases long term. They would have gradually leaked into space, molecule by molecule, until the Moon was airless again. The whole episode might have lasted only tens of millions of years, a blink in geological time, leaving no trace except perhaps subtle chemical signatures in rocks from that era. It's a strange thought. The Moon temporarily wearing an atmosphere like a borrowed coat, then losing it again, returning to the vacuum that defines it now. The Moon's surface contains compounds called agglutinates. tiny particles welded together by micrometeorite impacts. Lunar soil isn't like Earth's soil. It's full of strange particles called agglutinates, clumps where tiny grains of mineral and glass have been welded together by the heat of micrometeorite impacts. These form nowhere on Earth because they require vacuum, extreme temperature, and impacts energetic enough to melt materials without an atmosphere to slow them down. When a micrometeorite strikes lunar regolith, it vaporizes on impact, creating a tiny explosion that melts surrounding particles. The molten material splashes outward, incorporating rock fragments, mineral grains, and metallic iron vapor, then rapidly cools into glassy clumps. Over time, these agglutinates accumulate in the soil, making up a significant fraction of the regolith. Agglutinates are one of the markers scientists use to determine how long soil has been exposed on the surface. The longer the exposure, the more impacts it's experienced, the more agglutinates it contains. Mature soil exposed for millions of years is rich with them. Fresh material recently excavated by impacts has few. They're also a challenge for future lunar operations. Agglutinates contain tiny particles of metallic iron, making lunar soil slightly magnetic and even more abrasive than regular dust. They contribute to the soil's tendency to cling to everything, to get into mechanisms, to resist cleaning. They're a product of the Moon's unique environment, airless, bombarded, patient, creating materials that simply don't exist anywhere else. The Moon's role in stabilizing Earth's climate may have been crucial for the development of complex life. Earth's 23.5 degree axial tilt gives us our seasons, and the Moon keeps that tilt stable. Without the Moon, computer models suggest Earth's tilt would vary chaotically over millions of years, swinging anywhere from nearly 0 to 85 degrees. Think about what that would mean for climate. An Earth with no tilt would have no seasons, just an eternal gradient from hot equator to frozen poles. An Earth tilted 85 degrees would experience extreme seasons, each pole baking under months of continuous summer sun, then freezing in months of winter darkness. The climate would swing wildly, ice ages and warm periods alternating unpredictably. Complex life might not survive such chaos. Organisms need relatively stable conditions to evolve sophisticated adaptations. If the climate swings too wildly, too unpredictably, evolutionary strategies that work in one era become liabilities in the next. Stability, not perfect stability but predictable patterns, gives evolution time to work, time to develop complexity. The Moon provides that stability. Its gravitational influence damps out wobbles in Earth's rotation, keeps the tilt within a narrow range, ensures that our seasons remain predictable over geological timescales. This might have been essential for the evolution of complex life, for the development of ecosystems that depend on seasonal patterns, for the eventual emergence of intelligence. In this sense, the Moon didn't just give us tides and stabilized days. It might have given us the steady, predictable world necessary for complex life to flourish. We owe our existence, perhaps, to that ancient collision that created our companion. The Moon is the only world beyond Earth that humans have touched, a threshold we crossed in 1969 and have yet to cross again. On July 20th, 1969, Neil Armstrong descended the ladder of the lunar module Eagle, placed his foot on the surface of the Moon, and spoke words that have echoed through history. That's one small step for man, one giant leap for mankind. It was the first time a human being stood on a world that wasn't Earth, the first time we physically touched another celestial body. For all of human history up to that moment, we'd been confined to our home planet, looking up at the moon, dreaming about it, wondering what it would be like to go there. And then we went. 12 people total walked on the moon between 1969 and 1972. They collected rocks, conducted experiments, took photographs, planted flags, drove rovers across the surface, and then we stopped. The last person to walk on the moon was Eugene Cernan in December 1972, over 50 years ago. We've sent robots to Mars, to asteroids, to Saturn and Jupiter. We've built space stations and sent telescopes to orbit beyond the moon. But we haven't sent humans anywhere beyond low Earth orbit. The moon remains the farthest humans have ever travelled, the only other world we've ever touched. It waits there, patient as always, marked with our footprints and flags, our rovers and retroreflectors, waiting for us to return, to finish what we started, to take the next step beyond the one world we've ever called home. The moon is our first step outward, our proof that it's possible, our reminder that we reached another world once and could do so again. It sits in the sky each night, familiar and distant, calling us back to finish the journey we began, and then paused, waiting to see if we'll ever cross that threshold again and keep going, outward, to all the other worlds that wait beyond. And there we have it. 100 facts about the moon, our ancient companion, our first destination beyond Earth, our steady presence in the night sky for as long as there has been sky to look at. The moon is many things, isn't it? A mirror reflecting sunlight, a gravitational anchor stabilizing our planet's tilt, a museum preserving 4.5 billion years of solar system history in its craters and rocks, a future resource perhaps for the next chapter of human exploration, and always, always a source of wonder, that bright disk that's watched over our species since before we were a species, that guided us through dark nights, that marked our months and inspired our stories. We've learned so much about it. We've walked on it, brought pieces of it home, measured its distance to the millimeter using lasers and mirrors. We know its chemical composition, its internal structure, the details of how it formed from catastrophe. And yet it remains mysterious in the way all truly old things are mysterious, bearing witness to timescales we can barely imagine, existing in a state of patient permanence we'll never quite understand. Perhaps that's fitting. Perhaps the moon should remain slightly mysterious, slightly out of reach, even as we study it and eventually return to it. Some things are meant to be wondered about, to inspire questions more than answers, to remind us that the universe is older and stranger and more patient than we are. So tonight, if the sky is clear, look up. Find the moon, whatever phase it's in, crescent or full, waxing or waning. Remember that it's the only other world humans have ever touched. Remember that it's slowly drifting away, that it once had a magnetic field, that it rings like a bell when struck. Remember that it's keeping Earth stable enough for life to flourish, that it's pulling our oceans into tides, that it's covered in glass beads and ancient footprints and frozen lava flows. And maybe, just maybe, remember that all of this, all these facts, all this science, all this knowledge, doesn't diminish the moon's beauty, it enhances it. The more we know, the more remarkable it becomes that this scarred, ancient, patient world has been our companion for so long, watching quietly as we evolve from simple organisms into beings capable of understanding it, visiting it, and one day perhaps living there. Sweet dreams, night wanderer. The moon will be there when you wake, just as it's been there every morning for billions of years, waiting in the daylight sky, patient and eternal.